Look up at the night sky. Those points of light, those distant suns, seem eternal and unchanging. But each one has a birthday. Each one began its life in a place of profound darkness and quiet potential. A story of creation so immense it challenges our very understanding of time and space. For centuries, the birth of a star was the universe's best-kept secret, a process shrouded in veils of gas and dust, hidden from our view. But what if you could pull back those cosmic curtains? What if you could witness the very moment a star is born? That is the journey we begin together today. We are about to dive into one of the most fundamental and beautiful processes in the cosmos, unraveling 40 profound mysteries that surround star formation. This is not just a story about astrophysics. It is the story of our own origins. Every single atom in your body, the iron in your blood, the calcium in your bones, the oxygen you breathe, was forged in the nuclear furnace of a star that lived and died long before our sun was even a glimmer in a galactic cloud. We are quite literally stardust, and to understand how stars form is to understand where we came from. Our epic exploration will take us from the silent, frozen cradles of giant molecular clouds, where gravity's gentle pull first begins a billion-year dance, to the final, brilliant ignition that creates a new beacon in the dark. We will confront the fierce battles against magnetic fields, witness the spectacular jets that sculpt stellar nurseries, and question why the universe seems to favor the creation of countless small, dim stars over a few brilliant giants. We will investigate how a spinning cloud of gas avoids tearing itself apart, and how the chaotic turbulence within these clouds acts as both a creator and a destroyer. This is a narrative filled with drama on an unimaginable scale, where invisible forces shape destinies and the laws of physics play out in a cosmic theater light years across. The secrets we uncover will not only explain the lights in our sky, but will also reveal the fundamental forces that build galaxies and make planets, and perhaps life itself, possible. So prepare to have your curiosity ignited. This is more than a list of facts. It is a detective story, a deep dive into the heart of cosmic creation. We are setting out to answer the big questions that have puzzled astronomers for generations. What is the spark that triggers a cloud's collapse? How do stars regulate their own birth? And could we ever find another Earth orbiting a distant sun? The journey to unravel these 40 stellar mysteries begins right now. Let's step into the darkness and discover how the universe lights itself up. But before that grand performance can even begin, the universe must set the stage with the most fundamental of ingredients. Picture the darkest, most empty regions between the stars. They are not truly empty. They are filled with immense, shadowy structures known as giant molecular clouds. These are the primordial nurseries, the cosmic wombs where star formation is set into motion. To call them clouds is almost misleading. These are not the wispy, fleeting shapes we see in our sky. A single one of these cosmic entities can span light years across and contain enough material to form tens of thousands, even millions, of stars like our own sun. They drift slowly through the spiral arms of galaxies like our Milky Way, vast and silent and incredibly cold. Their temperatures hover just a few tens of degrees above absolute zero, a profound chill that is essential to the process about to unfold. Within these colossal clouds, the conditions are surprisingly complex. They are not simple, uniform balls of gas. Instead, they are dynamic and chaotic, threaded with intricate filaments and dense knots, more like a cosmic spider's web than a simple puff of smoke. This structure is key. The clouds are composed primarily of hydrogen molecules, the simplest and most abundant substance in the universe, but they are also laced with something else, tiny, microscopic grains of dust. These dust particles, made of carbon and silicate materials, are far more than just cosmic dirt. They act as a protective shield, blocking external starlight that would otherwise heat the gas and break apart the delicate molecules. More importantly, these dust grains provide surfaces where chemical reactions can occur, allowing the formation of more complex molecules, from simple carbon monoxide to the precursors of amino acids. It is within this frigid, dusty, and chemically rich environment that the first seeds of stardust are sown, and then there is the invisible architecture, magnetic fields. Woven throughout the galaxy are lines of magnetic force, and these threads are trapped within the molecular cloud. This magnetic tapestry is incredibly weak by earthly standards, but across such vast scales of space and time, it exerts a profound influence. It provides a subtle pressure that helps support the cloud against its own weight, a force that gently resists the inevitable pull of gravity. It is a delicate balance, a quiet standoff that can last for millions of years. But within this seemingly stable structure, tiny fluctuations are always at work. A slight ripple from a passing star, the shockwave from a distant supernova explosion, or simply the random churning of the cloud's own internal turbulence can create a small region where the gas becomes just a little bit denser than its surroundings. And in that moment, the balance is tipped. That pocket of gas, now feeling a slightly stronger gravitational pull from within, begins a slow, inexorable inward fall. This is the quiet prelude to the storm of creation, a place of immense potential energy waiting to be unleashed. So we have our stage set, a vast and quiet molecular cloud. But a cloud in equilibrium is just a cloud, it's not a star. For that billion-year dance of gravity to truly begin, something has to provide the first push, a cosmic nudge that upsets the delicate balance. This brings us to our very first, and perhaps most fundamental, mystery. What is the precise trigger that makes a cloud fall inward? After all, these clouds can drift for eons in a state of near-perfect balance, with internal pressure and magnetic fields gently holding gravity at bay. They are stable, but they are also pregnant with potential, waiting for a spark. Identifying that initial spark is like finding the single snowflake that starts an avalanche. Astronomers have several compelling suspects, each with its own compelling evidence. One of the most dramatic candidates is the shockwave from a supernova explosion. When a massive star reaches the end of its life and detonates, it blasts material outward at incredible speeds. This expanding shell of gas acts like a cosmic plow, slamming into a nearby molecular cloud. The force of this impact can compress the gas to critical densities, creating those dense pockets where gravity finally gains the upper hand. We even see evidence for this in our own galaxy, with beautiful, bubble-like structures where new stars are forming right on the edges of old supernova remnants. It's a story of stellar death giving birth to new life, a cycle of cosmic recycling on a grand scale. But a supernova isn't the only galactic event with enough power to stir things up. Consider the immense gravitational pull of an entire galaxy. When two galaxies pass near each other, or even collide in a slow-motion cosmic train wreck, their gravitational tides can stretch and squeeze the gas within them. This process, known as tidal compression, can trigger widespread star formation across vast regions. We see this spectacularly in so-called starburst galaxies, where the rate of star birth is hundreds of times faster than in our own Milky Way. These galactic encounters are like shaking a cosmic snow globe, agitating the gas and creating the perfect conditions for collapse. Even the regular rotation of a spiral galaxy like our own can play a role. As the galaxy spins, its spiral arms are not solid structures but rather density waves like traffic jams moving through the stars and gas. When a molecular cloud enters a spiral arm, it experiences a sudden increase in pressure, which can be enough to kickstart the collapse. This may be why we see the brightest, youngest stars so prominently aligned along the spiral arms. They are literally tracing out the regions of triggered star formation. Then there are the more internal, subtle triggers. Sometimes the catalyst isn't a dramatic external force but the cloud's own internal turbulence. These clouds are not serene and placid. They are chaotic and supersonic, with gas flowing in complex, unpredictable patterns. In this turbulent sea, random motions can sometimes converge, creating a region dense enough for self-gravity to take over. It's as if the cloud's own internal churning can, by sheer chance, create the seed of its own transformation. Another possibility is the simple collision of two smaller clouds. As they merge, their gas piles up at the interface, again reaching that critical threshold where gravity becomes the dominant force. The specific trigger matters immensely because it leaves a fingerprint on the resulting stellar nursery. A supernova-triggered region might produce a single, isolated cluster of stars with a very specific age. A galaxy collision, on the other hand, might ignite star formation simultaneously across an entire region, creating a fireworks display of stellar birth. By studying the patterns and ages of stars in a cluster, astronomers can often work backwards like cosmic detectives to determine what event set the whole process in motion. Solving this first mystery is the key that unlocks the entire sequence, revealing how the large-scale architecture of the galaxy directly influences the birth of its individual stars. But if that initial trigger provides the first nudge, what happens next inside the cloud is a story of beautiful, complex chaos. Imagine throwing a handful of pebbles into a still pond. The surface doesn't just sink smoothly. It erupts into an intricate pattern of ripples, waves, and intersecting circles. Now magnify that to a cosmic scale where the pond is a light-year-wide cloud of gas, and the pebbles are forces like supernova shockwaves and internal pressures. The result is not a calm, orderly collapse but a violently turbulent mess. This brings us to our second great mystery, the role of turbulence as a cosmic architect. Within a collapsing cloud, chaos doesn't just happen. It is a primary designer carving the cloud's structure in ways that gravity alone never could. The gas doesn't flow in a serene, uniform inward drift. Instead, it moves in supersonic motions, faster than the speed of sound within that medium, creating a complex, ever-changing web of swirling eddies, thin filaments, and dense knots. It's like a hurricane that's light years across, with winds that would dwarf anything our planet has ever experienced. This turbulence plays a deeply paradoxical role, acting as both a creator and a destroyer, a supporter and a challenger. On one hand, all that churning motion creates pressure. The random, high-speed movements of gas parcels act like millions of tiny battering rams, pushing outward and providing support against the relentless inward pull of gravity. In this way, turbulence can actually hold a cloud up, preventing it from collapsing too quickly. It's the cloud's internal energy, its fierce and chaotic heartbeat, that keeps it from simply imploding. But on the other hand, this same chaos is precisely what creates the seeds for future stars. When those supersonic flows collide, they can pile up gas into incredibly dense regions. Think of it like ocean waves crashing into each other, sending spray flying upward. In the cosmic cloud, these collisions create dense knots and filaments where the gas becomes hundreds of times denser than the surrounding material. In these localized pockets, gravity's pull becomes overwhelmingly strong, overwhelming the very turbulent motions that created them. So, turbulence giveth, and turbulence taketh away. It supports the cloud as a whole, but it also fragments it into the specific pieces that will become individual stars. The final outcome of a stellar nursery, how many stars it makes, and what sizes they will be hangs delicately on the balance between the energy of this turbulence and the power of gravity. Astronomers describe this with a key number called the virial parameter. If the turbulent energy is much greater than the gravitational energy, the cloud will simply shake itself apart and no stars will form. If gravity is too strong, the entire cloud might collapse monolithically into a single, gigantic star. But in most cases, we see a balance where turbulence and gravity are in a rough equilibrium. This perfect tension allows the cloud to fragment into a spectrum of cores, leading to the birth of a whole cluster of stars with a range of masses. It's this balance that likely explains why we get many small stars for every few large ones, a pattern we will explore in a later mystery. Advanced computer simulations are our best tool for understanding this chaotic dance. Researchers input the laws of physics and watch as virtual clouds evolve, their turbulent flows giving rise to stunningly realistic filamentary structures that look remarkably like those we see with telescopes like the Herschel Space Observatory. But the full picture is still elusive, simulating the immense range of scales from the size of the entire cloud down to the birth of a single star, pushes the limits of even our most powerful supercomputers. The exact way turbulence dissipates its energy, transferring it from large eddies down to smaller and smaller scales until it finally heats the gas, is a complex process that we are still working to understand fully. This inherent disorder is not a flaw in the system, it is a fundamental ingredient in the recipe for star formation. And as the densest knots begin their final collapse, they carry with them another invisible force that will profoundly shape their destiny. Now, as the chaotic turbulence carves the cloud into dense knots and filaments, setting the stage for collapse, another invisible and formidable force enters the fray. This is the cosmic battlefield of magnetism. Drifting through the galaxy, every molecular cloud is threaded with incredibly weak but pervasive magnetic fields, remnants of the galaxy's own primordial magnetic tapestry. As gravity begins to pull the gas inward, it doesn't just pull on the atoms, it pulls on these magnetic field lines, dragging them along for the ride. Imagine the cloud is like a vast bundle of elastic bands, with each band representing a line of magnetic force. As the cloud contracts, those bands are squeezed closer together, and just like a compressed spring, they push back. This magnetic pressure becomes a powerful force resisting the inward crush of gravity, creating a cosmic tug of war that can dramatically slow down the entire collapse process. In fact, without some way to overcome this magnetic support, many clouds might never collapse to form stars at all. This resistance is so significant that it fundamentally dictates the timeline of star formation, stretching what might be a rapid free fall into a slow, protracted dance that can last millions of years. This leads us to one of the most crucial and subtle processes in all of star formation, ambipolar diffusion. It sounds complex, but the concept is elegantly simple. The gas in a molecular cloud is not a uniform soup. It's a mix of charged particles called ions and neutral particles, which are just regular atoms and molecules. The key point is that the magnetic field lines are essentially frozen into the ionized gas. The charged particles are tied to the field and can't cross it. The neutral particles, however, don't feel the magnetic field directly. They are only interested in gravity's pull. So, what happens? As gravity pulls everything inward, the neutral particles try to fall straight toward the center. But the ions stuck to the magnetic field lines are held back, acting as an anchor. The result is that the neutral particles slowly diffuse past the ions, slipping through this magnetic scaffolding like sand trickling through a sieve. This gradual seepage allows the central, dense core to slowly build up mass while the magnetic field and the ions attached to it are left behind in the outer envelope. It's this slow leakage of neutral material that ultimately allows gravity to win, enabling the core to condense to the densities needed to form a star. Ambipolar diffusion is the universe's clever trick for overcoming magnetic support, a slow and steady process that unlocks gravitational collapse. Simultaneously, another magnetic phenomenon is at work: magnetic braking. Remember that tiny bit of rotation inherited by the cloud. As the cloud collapses, that spin increases dramatically due to the conservation of angular momentum. If left unchecked, this rapid rotation would fling the material apart long before a star could form. Magnetic fields provide a vital braking mechanism. The field lines anchored in the collapsing core can extend outwards into the slower rotating outer parts of the cloud, or even the surrounding interstellar medium. Think of it like stirring a cup of coffee with a spoon and then suddenly dipping the spoon into a thick jar of honey. The honey slows the spoon down. In the same way, the magnetic field acts like a cosmic spoon, transferring the core's rotational energy outwards, slowing its spin. This braking action is essential for allowing material to continue falling onto the growing protostar. The precise efficiency of this braking, however, depends on the complex geometry of the field and the environment, and it's a key factor in determining how fast the newborn star will ultimately spin. The invisible struggle between gravity, rotation, and magnetism therefore shapes not only the star's birth but its entire future character. Unraveling this magnetic interplay is fundamental to explaining the great diversity of stars we see, and it sets the stage for understanding the next great puzzle: why the universe seems to have a preferred recipe for building mostly small stars. Now, as we've seen the invisible forces of magnetism shape the collapse, a larger, more fundamental pattern emerges when we step back and look at the final product of a stellar nursery. It's a pattern so consistent it seems to be a universal rule of cosmic construction. When astronomers sense a star cluster, they don't find a random assortment of sizes. Instead, they discover a distinct hierarchy, a kind of cosmic pecking order. For every brilliant behemoth star that forms, a star 10 or even 100 times the mass of our Sun, there are orders of magnitude more average stars like our own. And for every Sun-like star, there is a veritable multitude of smaller, cooler, red dwarf stars. This predictable distribution of stellar masses at birth is what astronomers call the initial mass function, and its existence is our fourth great mystery. Why does the universe have such a strong preference for building small stars? The answer to this question isn't just an academic curiosity. It determines the very population of a galaxy, its light output, its chemical evolution, and even its potential for hosting habitable worlds. A universe that built mostly massive stars would be a vastly different and likely much shorter-lived place. So, what physical process dictates this cosmic assembly line? Scientists have two primary competing theories, each with its own compelling logic. The first theory points back to the turbulent nature of the molecular cloud itself. As we discussed, turbulence carves the cloud into a complex web of filaments and dense knots through a process called turbulent fragmentation. The idea here is that this chaos naturally produces many more small fragments than large ones. Think of it like shattering a large pane of glass. You'll end up with a huge number of tiny shards, a handful of medium-sized pieces, and only a few large chunks. In this scenario, the initial mass function is essentially set right at the very beginning during the fragmentation process. The distribution of core masses created by the turbulence then maps directly onto the final masses of the stars. The star's fate, in a sense, is sealed by the random, chaotic motions within the cloud before the core even begins its main collapse. The second major theory argues that the story isn't so simple. This idea, known as competitive accretion, suggests that the initial fragments are all born with relatively similar, low masses, but they are not born in isolation. They are crowded together in a dense cluster. In this cosmic daycare, the cores are all drawing from a shared reservoir of gas. Here, gravity plays a more dynamic and ruthless role. The slightly more massive cores, by virtue of their stronger gravitational pull, begin to steal gas from their smaller, weaker neighbors. It's a gravitational free-for-all where the rich get richer and the poor get poorer. In this model, a star's final mass isn't predetermined at birth, but is the result of a fierce competition for material. The few winners grow to become massive stars, while the vast majority of cores end up as small stars, having had their lunch stolen right out from under them. This would mean the initial mass function is an emergent property of the social dynamics within a young star cluster. Deciding between these theories is incredibly challenging because they make very similar predictions about the final outcome: a lot of small stars and a few big ones. The key to distinguishing them lies in the fine details, such as the precise relationship between the mass of a dense core and the mass of the star that forms inside it. Do we see evidence of cores being gravitationally stripped by their larger siblings? With powerful observatories like the Atacama Large Millimeter Array, or ALMA, astronomers can now peer into nearby stellar nurseries with unprecedented resolution, mapping the distribution of gas around individual protostars, searching for the telltale signs of this competitive feeding. The answer likely involves a combination of both processes, with turbulence setting the initial stage and competitive accretion fine-tuning the final masses in the densest cluster environments. This pattern, this universal tendency toward smallness, has a direct consequence. It means that the most common outcome of the star formation process is not a brilliant sun-like star, but a solitary, small fragment, a single dense core now cut off from the hustle and bustle of the cluster, beginning its own quiet journey toward ignition. Now, as the gravitational free-for-all of the cluster settles and a single dense core breaks away, we enter a more intimate and focused chapter in the story of star birth. This core, now cut off from the competitive chaos of its siblings, begins a period of solitary collapse. In the quiet of its own gravitational field, the physics becomes, in theory, beautifully simple. Imagine a perfectly spherical ball of gas, cold and dark, sitting in the emptiness of space. Under the influence of its own weight, it begins to fall inward uniformly from all directions. This idealized scenario is what astrophysicists describe with the classic Larson-Penston solution, a mathematical model that predicts how the density and velocity of the gas should change as the collapse proceeds. It's a picture of elegant, symmetrical contraction, a straightforward gravitational downfall, but the universe has a knack for complicating beautiful theories. The reality is that no core is ever perfectly spherical or perfectly still. Remember that tiny bit of rotation, that faint whisper of spin inherited from the grand rotation of the galaxy itself. As the core contracts, this spin becomes the most important actor in the drama. The principle of conservation of angular momentum takes center stage. Just as a figure skater spins faster when they pull their arms in, the collapsing cloud spins faster and faster as it shrinks. This increasing rotation fundamentally breaks the perfect symmetry. Material falling in along the rotation axis, the imaginary pole running through the center can fall straight down, but material trying to fall in from the equator finds itself whipping around the center so fast that it can no longer fall inward directly. Instead, it goes into orbit. This is the moment of transformation, the birth of a disk. The once spherical core begins to flatten, squashing down at the poles and bulging at the equator, slowly taking on the shape of a spinning disk, much like a ball of pizza dough being spun into a flat crust. This marks a critical transition. We are no longer dealing with a simple infalling envelope of gas. Now a complex structure emerges, a central, dense concentration of mass that will become the protostar itself, surrounded by a vast, swirling, flattened reservoir of gas and dust known as the accretion disk. This disk is not just a byproduct, it is the essential channel through which the growing star will be fed. Material can no longer fall directly onto the protostar from all directions. Instead, it must first join the disk, slowly losing energy and angular momentum as it spirals inward in a cosmic ballet before finally being accreted onto the central object. This isolated gestation period, this quiet time of core collapse and disk formation, is arguably one of the most crucial phases. The properties of the disk, its mass, its size, its temperature, are set during this time, and these properties will dictate everything that follows. They determine the final mass of the star, the rate at which it grows, and most importantly, they set the stage for the entire future planetary system. The dust grains within this disk are the building blocks of planets, and how they behave is entirely governed by the structure and dynamics of the disk itself. The initial conditions established during this solitary conception are therefore the blueprint for a potential solar system, a legacy that will last for billions of years. But this elegant process of a spinning cloud flattening into a disk presents one of the most critical problems in all of star formation, a true make-or-break moment for any future sun. The issue is one of spin, a property known as angular momentum. Every molecular cloud core, simply by virtue of being part of a rotating galaxy, possesses a tiny, almost imperceptible amount of rotation. It might be a slow, lazy turn that takes millions of years to complete a single revolution. This seems insignificant, but as the cloud begins its gravitational collapse, a fundamental law of physics takes over, the conservation of angular momentum. This principle dictates that as an object gets smaller, it must spin faster to conserve its rotational motion. You can see this yourself when an ice skater pulls their arms in during a spin. Their body contracts and they whirl around at a dizzying speed. Now apply this to a cloud of gas that's collapsing from a size larger than our entire solar system down to a single star. The math is terrifying. If that initial, gentle spin were conserved perfectly, the core would accelerate to such an incredible rate long before it reached stellar densities that the centrifugal force at its equator would overpower gravity, flinging the material outward and halting the collapse entirely. The star would be stillborn, its potential scattered back into the void, and yet we are surrounded by stars. Clearly, they found a way to solve this problem. The great mystery is not if the spin is shed, but precisely how. How does a collapsing cloud put on the brakes? The leading solution to this cosmic puzzle is a brilliant two-step process involving the very disk that the rotation creates. The formation of the accretion disk is not just a consequence of the spin, it is the essential component of the braking system. Think of the disk as a vast cosmic flywheel. As material spirals inward through the disk, it doesn't all move at the same speed. The inner parts of the disk orbit much faster than the outer parts, creating a tremendous amount of shear, a difference in velocity between adjacent layers. This shear, combined with magnetic fields and other forms of viscosity, creates friction. This friction does two things. It heats the disk, causing it to glow in the infrared, and crucially, it allows angular momentum to be transferred outward. It's a bit like a row of people on a rotating platform. If the person in the center wants to slow down, they can grab the hand of the next person, transferring some of their spin outward. That second person then does the same to the third, and so on. In the disk, the inner, fast-spinning material effectively hands off its excess angular momentum to the outer, slower-moving material, which then moves to an even wider orbit. This process allows the inner material to slow down just enough to continue its journey onto the waiting protostar. The disk, therefore, acts as a temporary storage unit for the star's spin, a buffer that prevents a catastrophic speed up. But this only solves half the problem. If angular momentum is simply transferred to the outer disk, that outer disk would eventually spin itself apart. There must be a way to remove this rotational energy from the system entirely. This is where one of the most spectacular phenomena in the cosmos comes into play: bipolar outflows. As the young protostar and its inner disk spin, their powerful magnetic fields become wound up like a coiled spring. These twisted field lines act like a slingshot, launching twin jets of material perpendicular to the disk, shooting out from the protostar's poles at speeds that can reach hundreds of kilometers per second. This is the system's escape valve. The material in these jets carries a tremendous amount of angular momentum away with it, ejecting it far out into the interstellar medium. It's a brilliant cosmic trade-off. The protostar sacrifices a small amount of its mass to rid itself of the destructive spin that would otherwise prevent it from growing. These jets are not a gentle breeze. They are focused hypersonic beams that can travel for light years, plowing into the surrounding cloud, heating the gas, and creating shock waves that can even trigger the formation of new stars elsewhere. They are both a signature of a young star's struggle and a sculpting force in their own right. The precise mechanics of how the magnetic fields launch and collimate these jets, however, remain one of the most active and challenging areas of astrophysical research. There are competing models, such as the magnetocentrifugal mechanism, where gas is flung out along magnetic field lines like beads on a rotating wire, or processes driven by intense magnetic pressure near the star's surface. Observing the innermost regions where this happens is incredibly difficult, as it occurs on scales smaller than our own solar system and is hidden behind thick veils of dust. The efficiency of this braking system also has direct consequences for the star's future. A star that sheds its angular momentum effectively will end up as a slow rotator, like our Sun, which takes nearly a month to complete a single rotation. A star that is less efficient at braking might spin 10 or even 100 times faster, which would generate a much more powerful magnetic field and intense stellar activity, profoundly affecting any potential planets in orbit. The solution to the angular momentum problem is therefore not just about star birth. It's about setting the stage for the entire character and longevity of a stellar system, a legacy written in the interplay between spin, disks, and the spectacular jets that light up the nursery. And so, the very process that threatens to tear a young star apart, its furious spin, also gives rise to one of the most breathtaking sights in the cosmos. As the protostar and its inner accretion disk whirl at ever-increasing speeds, their entangled magnetic fields become stretched and twisted into a configuration akin to a colossal spring, storing immense energy. This pent-up force cannot be contained forever. It finds its release in a spectacular and violent exhalation, the birth of bipolar outflows. These are not gentle winds. They are narrowly focused jets of plasma, superheated gas charged with particles, that erupt from the protostar's poles at velocities that can approach a fraction of the speed of light. shooting out in opposite directions, perfectly aligned with the star's rotation axis. These jets can stretch for several light years, carving vast tunnels through the surrounding molecular cloud. They are a definitive signature of youth, a cosmic announcement that a star is fighting its way into existence. The mechanism behind these cosmic cannons is a masterpiece of magnetic engineering. The most widely accepted model is the magnetocentrifugal launch. Imagine the inner region of the accretion disk, a seething, hot zone where material is spiraling inward at a frantic pace. Here, the protostar's powerful magnetic field lines are frozen into this ionized gas. Because the inner disk is spinning so rapidly, these field lines act like the rigid arms of a merry-go-round. Gas from the disk becomes trapped along these lines and is flung outward, not unlike how a bead on a spinning wire is hurled away from the center. This process efficiently extracts rotational energy from the disk. But to create a jet, this flung material must be focused or collimated into a tight beam. This is where the complex geometry of the magnetic field itself comes into play. The field lines are thought to converge into a narrow funnel above and below the star's poles, channeling the erupting material into two opposing, incredibly precise streams. It's a natural particle accelerator of staggering power, all driven by the fundamental interplay between rotation and magnetism. The importance of these jets, however, goes far beyond their stunning appearance. They are an essential part of the star's growth strategy, solving the critical angular momentum problem we just explored. Think of the jets as the star's waste disposal system for spin. The material being ejected carries with it a disproportionate amount of angular momentum. By violently throwing a small fraction of its mass away, the young star system rids itself of the destructive rotational energy that would otherwise prevent it from accreting more mass. It's a brilliant trade-off: sacrifice a little to gain a lot. This allows gas from the outer disk to continue spiraling inward, eventually reaching the protostar and adding to its bulk. Without this mechanism, star formation would be far less efficient, and many potential stars might never reach their full mass. Furthermore, these outflows play a profound role in sculpting their own nursery. When the high-speed jets slam into the slower-moving gas of the surrounding molecular cloud, they create powerful shock waves. These shocks heat the ambient gas, causing it to glow brightly in specific wavelengths of light, which astronomers can detect. The jets essentially blast away the cocoon of gas and dust that enshrouds the newborn star, effectively clearing the room around it. This violent interaction does more than just create a pretty light show. It regulates the star-forming environment. By dispersing and heating the nearby gas, the jets can shut down further star formation in their immediate vicinity, preventing the birth of nearby siblings. In other cases, the shock waves from a jet might compress other pockets of gas in the cloud, triggering a new round of collapse and star birth elsewhere. This dual role, both as a destroyer and a creator, makes bipolar outflows a key agent of feedback, a force that shapes the structure and population of an entire stellar cluster. The story of a star's birth is therefore not a solitary event, but a dynamic interaction that leaves a lasting imprint on its cosmic neighborhood for millions of years. So, with the star's furious spin tamed by the spectacular jets, the stage is now set for the true engine of growth to emerge. The material that isn't flung out into space or pulled directly onto the protostar finds a stable, organized home in a magnificent structure, the accretion disk. This is no mere cloud of debris. It is a vast, spinning carousel of gas and dust, a cosmic construction site that will ultimately determine the star's final size and the entire architecture of its future planetary system. Think of it as the protostar's personal pantry and a planetary blueprint all in one. For the next several million years, this disk will be the central character in the story, a dynamic and complex entity governed by physics that challenges even our most powerful supercomputers. The very existence of this disk is a direct consequence of that conserved angular momentum we discussed. As the cloud collapsed, its spin forced the material to flatten into this pancake-like shape. But the disk is far from a simple, serene whirlpool. It is a place of extreme and competing forces. At its heart lies one of the great puzzles of astrophysics. How does material actually move inward? After all, each particle of gas and dust in the disk is in a stable orbit around the central protostar, held in place by gravity, just like the planets around our Sun. For that material to spiral inward and feed the growing star, it must somehow lose orbital energy. This is where a seemingly mundane concept, viscosity, or internal friction, becomes the star's best friend. In a perfectly smooth, ideal fluid, there would be no friction, and the disk would remain a stable, non-accreting ring. But real disks are messy. They have turbulence, likely generated by a powerful phenomenon called the magnetorotational instability. This instability occurs when weak magnetic fields within the ionized gas of the disk get wound up by the difference in rotation speed between the inner and outer regions. This winding creates a magnetic tension that stirs the gas into a froth of chaotic motion, creating the effective friction needed to allow the gas to lose energy and drift slowly inward. This process of accretion is not gentle. As the gas spirals down through the disk, it releases a tremendous amount of gravitational potential energy. This energy doesn't just disappear, it is converted into heat through the very friction and turbulence that drives the flow. The inner regions of the disk, close to the hot, young protostar, can reach temperatures of thousands of degrees, causing the dust grains to evaporate entirely. Farther out, the disk is cooler, allowing ices to form on the dust grains. This temperature gradient creates distinct chemical zones that will later determine the composition of planets that form at different distances from the star. The disk, therefore, is not a static blueprint but a living, evolving system, glowing brightly in the infrared as it processes the raw material of a solar system. The structure and evolution of this disk are absolutely paramount. Its total mass sets an upper limit on how big the star can grow and how much material is available for planets. Its size determines the scale of the future planetary system, and perhaps most importantly, its lifetime sets a strict deadline. Observations tell us that the gas in these protoplanetary disks dissipates within a few million to 10 million years. This means the window for forming gas giant planets like Jupiter and Saturn, which must scoop up vast atmospheres before the gas is gone, is incredibly short. The mechanisms for this dispersal are thought to be a combination of the star's own intense radiation blowing the gas away, known as photoevaporation, and the ongoing accretion onto the star itself. Every detail of the disk's physics, from the strength of its magnetic fields to the size of its dust grains, contributes to the final outcome. The story of this single structure is, in essence, the story of how a star completes its assembly and how the seeds of worlds are sown, a process that begins in the deepest, most hidden phase of all. And so, after the dramatic launch of jets and the formation of the feeding disk, we arrive at the true beginning of a star's observable life, an object so young and hidden it represents the ultimate challenge for astronomers. This is the Class 0 protostar, the universe's best-kept secret, a stellar embryo in its very first stages of assembly. Imagine trying to observe a seed buried deep within the soil, shrouded in earth, long before any green shoot breaks the surface. That is precisely the challenge we face with a Class 0 object. It is not merely surrounded by a thin haze, it is completely engulfed within a massive, dense, and cold envelope of gas and dust, a cocoon so thick that not a single photon of visible light can escape. To peer inside this cosmic womb, we cannot use ordinary telescopes. Instead, we must rely on the long wavelengths of the electromagnetic spectrum, specifically submillimeter and infrared light. These longer waves, much like radio signals, can penetrate the dusty shroud, allowing us to detect the faint thermal glow of the cold dust and the unique signatures of molecules within the envelope. It is a form of astronomical sonogram, giving us a blurry but revolutionary glimpse into the earliest moments of stellar gestation. What makes this stage so critically important is that it captures the star in its most rapid phase of growth. This is the protostar's main accretion episode, a cosmic growth spurt where it is voraciously pulling in material from its surrounding envelope at a breathtaking rate. The vast majority of the star's final mass is accumulated during this relatively short-lived Class 0 period. At the very heart of this infalling chaos, a central object has just begun to take shape. It's not yet a true star in the sense that it's powered by nuclear fusion. That milestone is still millions of years away. Instead, its warmth comes from a different source, the sheer violence of its birth. The energy released by material crashing onto its surface at hypersonic speeds generates immense heat, making the core glow a dull red even as it remains hidden from direct view. This is an object defined by potential, a concentration of mass that has just tipped the scales from being a collapsing cloud to a bona fide stellar predecessor. Studying these hidden embryos provides the most stringent tests for our theoretical models of star formation. The properties we can measure, even indirectly, are like fingerprints left at the scene of a cosmic crime, telling us exactly how the collapse unfolded. For instance, the strength and structure of the bipolar outflows are a direct probe of the magnetic engine at the protostar's core. A powerful, well-collimated jet suggests a strong magnetic field and an efficient angular momentum transfer mechanism, just as our theories predict. Conversely, a weak or misaligned outflow might point to complexities we haven't yet accounted for. Similarly, measuring the mass of the infalling envelope compared to the mass of the central protostar itself is a crucial diagnostic. In a true Class 0 source, the envelope mass should still be greater than the mass of the central object, a sign of youth and a large reservoir of fuel still left to consume. As astronomers use powerful instruments like the Atacama Large Millimeter Array to weigh these components with incredible precision, they can check their simulations against reality, refining our understanding of how gravity, rotation, and magnetism conspire to build a star. The transition out of this hidden embryonic phase is a significant evolutionary step. As the protostar continues to feed, its intense radiation and powerful winds begin to push back against the infalling material. The envelope is gradually consumed, either accreted onto the star or blown away by its increasing activity. The cocoon thins, and the object evolves into a Class 1 protostar. At this point, the central engine becomes more directly visible, and the system begins to look more like a classic young star with a prominent protoplanetary disk. Therefore, the brief Class 0 window is our only chance to witness the initial conditions of star birth in their purest form, before feedback from the star itself forever alters the landscape. Capturing this fleeting moment is essential if we are to understand the complete story, from a silent cloud to the brilliant, visible object we recognize as a star. But after the furious feeding frenzy of the Class 0 and Class 1 phases subsides, a young star does not simply settle into a quiet life. Instead, it enters a period of tumultuous adolescence, a phase of stellar development as dramatic and transformative as any in a star's life. This is the era of the Tauri star, named after the first such object identified in the constellation Taurus. If the protostar phase was the star's infancy, hidden and rapidly growing, then the Tauri phase is its toddlerhood, a time of energetic outbursts, magnetic tantrums, and powerful growing pains. The star has, for the most part, finished accreting the bulk of its mass from the surrounding disk. It has gathered the material it will have for its entire lifetime. Yet, it has not yet achieved the final, stable state of a main sequence star like our Sun. It is still contracting under its own gravity, slowly shrinking and heating up until its core reaches the critical temperature and pressure needed to ignite sustained hydrogen fusion. This journey toward stability is anything but calm. Tauri stars are notoriously variable and magnetically hyperactive. Their surfaces are roiling with starspots far larger and more numerous than any sunspot on our Sun, causing their brightness to fluctuate significantly as they rotate. They unleash violent flares and emit intense X-ray radiation, a testament to their tangled and powerful magnetic fields. These fields also drive fierce stellar winds, outflows of charged particles that stream away from the star at high speeds. This entire cacophony of activity is powered by the star's rapid rotation and its ongoing gravitational contraction. The energy released as the star slowly shrinks is converted into heat, magnetic field generation, and the violent outbursts that characterize this stage. It's a star finding its footing, learning to balance its immense energies before settling into the long, steady burn of adulthood. The significance of the Tauri phase, however, extends far beyond the star itself. It is a critical juncture for any potential planets forming in the system. The protoplanetary disk that once fed the star is still present, but it is now living on borrowed time under a hostile sky. The star's intense ultraviolet and X-ray radiation bombards the disk, particularly the inner regions. This high-energy light heats the gas in the disk, giving individual molecules enough energy to escape the star's gravity altogether in a process known as photoevaporation. Think of it as the star using its own powerful light to blow away the very building blocks of future planets. Simultaneously, the strong stellar winds act like a constant, abrasive sandblasting, stripping material from the disk's surface. This dual assault sets a strict deadline for the formation of gas giant planets. A world like Jupiter, which requires a massive gaseous envelope, must form its solid core and accrete its gas atmosphere before the protoplanetary disk is completely evaporated and blown away by the tantrums of its toddler star host. For smaller, rocky planets like Earth, the Tauri phase is equally formative, but in a different way. The fierce radiation can selectively evaporate lighter, volatile elements from the dust grains and planetesimals in the inner disk, potentially altering their final chemical composition. It's possible that the intense activity of our own Sun during its Tauri stage played a role in sculpting the inventory of materials that eventually coalesced into the inner planets. Studying these young, active stars, therefore, provides a direct window into the early history of our solar system. By observing the interactions between a Tauri star and its disk, we can piece together the environmental conditions that shaped the worlds around us, understanding how the violence of stellar youth can either forge or frustrate the birth of planets. This tempestuous period, while chaotic, is an essential rite of passage, a final turbulent chapter before the star achieves the lasting equilibrium that defines its longest and most stable phase. After the tempestuous tantrums of the Tauri phase, a young star embarks on the final leg of its formative journey, a multi-million-year pilgrimage toward a state of perfect cosmic balance. This ultimate destination is known as hydrostatic equilibrium, and achieving it is the defining moment when a true star is born. imagine a perpetual, elegant tug of war where the two opponents are perfectly matched. On one side, you have the relentless inward crush of gravity, the star's own immense weight constantly trying to pull everything toward the center. On the other side, you have the powerful outward push of thermal pressure generated by nuclear fusion in the core. When these two titanic forces finally equalize, the star stops contracting. It finds its size, its shape, and its destiny. This stable condition is what astronomers call the main sequence, and it's where a star will spend the overwhelming majority of its life, burning hydrogen into helium in a steady, predictable manner. The path a star takes to reach this stable adulthood is beautifully mapped on one of the most important tools in all of astronomy, the Hertzsprung-Russell diagram. This isn't a map of the sky, but rather a graph that plots a star's luminosity against its surface temperature. For a star like our Sun, this journey is a slow, graceful drift across the diagram. It begins its life as a contracting protostar on the right side of the graph, relatively cool and very large, meaning it's quite luminous despite its low temperature because of its enormous surface area. As it continues to contract under gravity, it heats up, but because it's shrinking, its surface area decreases, which affects its brightness in a competing way. The star's path, known as the Hayashi track, is initially a near vertical descent, meaning it gets hotter without changing its luminosity much. Then, as its internal heat transport becomes more efficient, it shifts to a more horizontal path, the Heni track, steadily increasing in temperature and luminosity until it finally, quietly settles onto the main sequence. For a solar mass star, this entire process is a patient one, taking roughly 30 million years. It's a cosmic coming-of-age story, a transition from the volatile dependence on gravitational contraction for energy to the mature, self-sustaining power of core fusion. However, this journey is not one size fits all. The mass of a star is the single most important factor dictating its entire life story, and the path to the main sequence is no exception. A star with less than half the mass of the Sun, a red dwarf, takes a much longer, slower route. Its gravitational contraction is more gentle, and it takes hundreds of millions of years, even up to 1 billion, to finally heat its core enough to ignite sustained hydrogen fusion. On the other hand, a more massive star, say twice the mass of the Sun or more, is in a tremendous hurry. Its greater weight creates far higher core pressures and temperatures from the start, allowing it to ignite fusion in a blisteringly short time, sometimes in as little as 100,000 years. These stellar thoroughbreds essentially blast onto the main sequence, their immense gravity and furious fusion rates setting them up for short, brilliant lives. The precise route each star takes, the subtle kinks in its track across the Hertzsprung-Russell diagram, also hold clues to its accretion history, such as whether it experienced periods of rapid mass gain or violent outbursts during its Tauri phase. Reaching the main sequence is the conclusion of the star formation process as we define it. It's the moment a celestial object graduates from being a young stellar object to a bona fide star. But this stable adulthood is only the beginning of a new, even longer chapter. The star's position on the main sequence is fixed primarily by its mass, determining its color, brightness, and lifespan. Our Sun, comfortably in the middle, will reside there for roughly 10 billion years. This long, stable period is the reason life had a chance to arise on Earth. It provides the constant, predictable energy source necessary for evolution to work its slow magic. The achievement of hydrostatic equilibrium is therefore not just a physical milestone, it's a prerequisite for cosmic habitability. But while stars like our Sun follow a relatively serene path to this stability, the universe has a far more extreme and violent method for building its true giants, a process that defies the very forces that threaten to halt it. But while stars like our Sun find a relatively serene path to stability, the formation of a truly massive star is a different story entirely, a frantic, violent race against the laws of physics themselves. Imagine a young protostar just beginning to shine. For a star destined to be like our Sun, the light it emits is a gentle warmth, not yet strong enough to interfere with the rain of gas still falling onto it from the surrounding cloud. But for a protostar aiming for true greatness, a mass 8, 10, or even 100 times that of the Sun, this light becomes its greatest enemy. As it rapidly grows and its core heats up, it begins fusing hydrogen at a ferocious rate. This furious fusion generates an overwhelming torrent of radiation, light particles streaming outward from the core with immense energy. This creates an outward force called radiation pressure, and for a massive star, this pressure is so powerful that it literally pushes back against the infalling material, like a cosmic wind trying to blow out a candle by reversing the very flow of wax. This creates a fundamental barrier. The more mass the star gains, the brighter it shines, and the harder it pushes away the gas it needs to grow even further. So how in the universe does any star overcome this self-imposed limit to become a behemoth? The leading theory suggests that these stars cheat the system through geometry. Instead of a simple spherical collapse, they likely rely on highly non-spherical accretion, funneling material onto their surfaces in a more targeted way. The key, once again, is the accretion disk. Picture a massive protostar shrouded in a thick, dusty envelope. Material falls inward from all directions, but as it nears the star, it is channeled into a dense, swirling disk. This disk acts as a protective shield, absorbing the star's intense radiation along its equator. The radiation, seeking the path of least resistance, then blasts outwards above and below the disk, escaping through the poles in a phenomenon known as radiation-driven bipolar cavities. This creates a scenario where the equator is dark and cool, allowing gas from the inner edge of the disk to silently rain down onto the star's surface, while the poles are flooded with blinding light. It's a clever cosmic workaround, like building a covered tunnel to walk through a torrential downpour. The disk provides a sheltered pathway for mass to reach the star despite the hurricane of radiation trying to repel it. Another, more dramatic possibility is that the largest stars form through stellar collisions and mergers. In the incredibly dense cores of massive star clusters, young protostars are packed together like commuters in a crowded subway car. In such an environment, close gravitational encounters are inevitable. It's possible that smaller stars, each having formed in the traditional way, could be gravitationally drawn together and merge, creating a single, more massive object in a sudden, violent event. This process of coalescence could potentially build up a star's mass very quickly, perhaps faster than the radiation pressure can react to shut it down. While this scenario is more speculative and likely rarer than accretion through a disk, it highlights the extreme and dynamic conditions within these stellar factories. The truth may involve a combination of both mechanisms, with rapid disk accretion doing the bulk of the work, punctuated by occasional mergers that provide a final mass boost. This entire process is not only violent but also incredibly swift and secretive. A massive star lives its entire life in the fast lane. It must form quickly, in perhaps just 100,000 years, a mere blink of an eye compared to the millions of years it takes for a sun-like star to form. And because it forms so rapidly, it spends almost its entire gestation period deeply embedded within the dense, opaque core of its natal cloud. This makes observing the birth of massive stars one of the most challenging tasks in astronomy. We cannot see them with optical telescopes. They are hidden behind impenetrable walls of dust. It is only with advanced infrared and radio observatories, like the James Webb Space Telescope and the ALMA array, that we can begin to peer into these nurseries. We see the intense heating of the surrounding dust, the powerful outflows, and the telltale signs of massive disks, but the central engine itself remains elusive. The formation of these stellar giants is a rapid, intense, and deeply hidden process, but its impact is felt across the cosmos, as the lives and deaths of these massive stars ultimately shape the evolution of entire galaxies. But the story of a star's birth is rarely a solitary one. While we've followed the journey of a single core collapsing in relative isolation, this is not the typical experience for most stars in the universe, including our own Sun. The grand reality is that stars are profoundly social beings, born in bustling, crowded neighborhoods known as stellar clusters. These clusters are cosmic metropolises, containing anywhere from a few hundred to several 100,000 stellar siblings, all emerging from the same giant molecular cloud. This dense environment transforms the serene process of stellar gestation into a dynamic and often hazardous communal event. The central question we face is whether this cluster environment acts as a nurturing cradle, providing benefits to its young stars, or if it's a dangerous and disruptive neighborhood that hinders their development and the formation of their planetary systems. The most immediate hazard in a crowded cluster is the simple, relentless pull of gravity from nearby stars. In a sparse region, a young protostar can hold onto its expansive protoplanetary disk, the raw material for future planets for millions of years. But inside a dense cluster, a close encounter with a passing sibling star is not a rare event. It's a statistical certainty. When two young stars pass near each other, their gravitational fields interact like tidal forces. This gravitational tug of war can have dramatic consequences. It can strip away the outer portions of a protoplanetary disk, dramatically truncating its size and limiting the amount of material available for planet formation. In more extreme cases, a very close flyby can completely destabilize the disk, warping it or triggering the premature formation of planetesimals in chaotic, eccentric orbits. The most violent encounters can even fling a star entirely out of the cluster, creating a runaway star destined to wander the galaxy alone, its disk and any potential planets severely compromised by the traumatic ejection. Beyond these gravitational threats, there is an even more pervasive danger: radiation. The first stars to form in a cluster are often the most massive ones because they evolve and ignite their fusion engines with breathtaking speed. These massive stars are like the bullies of the stellar nursery, pouring out immense amounts of intense ultraviolet radiation. For the smaller, slower-forming stars around them, this radiation is a destructive force. It bathes their protoplanetary disks in a harsh, energetic light that heats the gas, giving molecules enough energy to escape the star's gravity. This process, known as photoevaporation, effectively boils away the disk from the outside in. Since gas giant planets like Jupiter must form quickly before the gas disk dissipates, this external photoevaporation can slam the window of opportunity shut, preventing the formation of such planets around many stars in the cluster. The inner, rocky planet-forming region might survive, but its chemical composition could be altered by the intense radiation, potentially stripping away water and other volatile compounds. Yet for all these dangers, the cluster environment might not be entirely hostile. There is a compelling argument that this crowded birth could actually be beneficial. The same shock waves and compression fronts from massive stars that photoevaporate disks can also trigger a second wave of star formation in nearby pockets of gas, potentially increasing the overall efficiency of the cloud's conversion into stars. Furthermore, the intense radiation field, while destructive to disks, also helps to clear away the leftover gas from the cluster much faster than would happen naturally. This rapid gas removal can actually stabilize the cluster sooner, preventing further disruptive gravitational encounters and allowing the remaining stars and their planetary systems to settle into a more peaceful existence. For a star like our Sun, being born in a cluster might have meant its disk was truncated, perhaps explaining why we lack a super-Earth or a hot Jupiter close to our star. But that same truncation and the early removal of gas could have allowed the inner rocky planets to form in a relatively calm environment, free from the later gravitational chaos that might have scattered them. The cluster, therefore, might be a place of both creation and destruction, a cosmic crucible that forges the most common types of planetary systems by subjecting them to a rigorous early test. The answer to whether it is a help or a hindrance likely depends on a star's specific location within the cluster and the timing of its birth relative to its more massive siblings. But the profound influence of a star does not end with its violent ejection from a cluster or the dispersal of its siblings' disks. The very act of a star's birth, especially for the most massive among them, sets in motion a cycle of cosmic cause and effect that reverberates across the galaxy. This brings us to a mystery of truly grand scale, the feedback loop, the process by which stars quite literally regulate their own birth. Up until now, we've largely considered star formation as a process that happens to a cloud, driven by external triggers or internal instabilities. But the reality is far more dynamic. Star formation is not a one-way street. It is a profoundly self-regulating process. The moment the first massive stars ignite within a stellar nursery, they cease to be passive products and become powerful actors, reshaping their environment with consequences that can last for millions of years. The most immediate and dramatic agent of this feedback is the intense radiation from massive stars. A star just a few times more massive than our Sun emits a torrent of high-energy ultraviolet photons. This radiation is so powerful that it has the ability to rip electrons away from hydrogen atoms, a process called ionization. Around these brilliant behemoths, vast regions of ionized hydrogen gas, known as H-II regions, begin to form. The classic example is the Orion Nebula, a glowing cloud visible to the naked eye that is the illuminated surface of a much larger molecular cloud. The gas inside an H-II region is heated to temperatures of thousands of degrees, causing it to expand violently. This expansion creates a powerful shock wave that plows into the surrounding, colder molecular cloud like a cosmic bulldozer. And here lies the beautiful paradox of stellar feedback. This advancing shock front can have two opposing effects, a true Jekyll and Hyde personality. On one hand, it can slam into a quiet, stable region of the cloud, compressing the gas to such a degree that it triggers a new wave of gravitational collapse and star formation. We see this vividly in space telescopes images, where the edges of these bright bubbles are often lined with the next generation of young stellar objects, their birth directly catalyzed by their brilliant older siblings. It's a story of stellar life begetting more life. On the other hand, that same expanding bubble can be an agent of destruction. If the shock wave hits a smaller, more tenuous cloud, or if it continues to expand unchecked, it can simply blow the cloud apart. The immense pressure and heat can tear molecules apart and disperse the gas back into the diffuse interstellar medium, effectively shutting down any potential for star formation in that area for eons. The ultimate form of this dispersive feedback comes from the most massive stars, which live fast and die young. After a few million years, a mere blink in cosmic time, these stars exhaust their nuclear fuel and explode as supernovae. The death of a massive star is an event of almost unimaginable power, unleashing in a single instant more energy than our Sun, will produce in its entire 10 billion-year lifetime. The blast wave from a supernova travels outwards at thousands of kilometers per second, sweeping up interstellar material, enriching it with heavy elements forged in the star's core, and during the explosion itself elements like the iron in our blood and the calcium in our bones. This ejected material, now laced with these metals, will eventually become part of future molecular clouds, making the next generation of stars and planets more chemically complex. But like the Roman II regions, the supernova shock wave is a double-edged sword. It can compress gas and trigger star formation, but it can also violently disrupt and disperse nascent stellar nurseries, potentially tearing apart protoplanetary disks and halting the growth of young stars. This intricate dance of creation and destruction is not a minor side effect. It is the primary governor that controls the rate of star formation across an entire galaxy over cosmic time. Without this feedback, our models suggest that galaxies would convert their gas into stars in a brief, furious burst, exhausting their fuel supply and leaving behind a red and dead galaxy populated only by long-lived low-mass stars. Instead, what we observe is that star formation is a slow, sustained process. Feedback acts as a cosmic thermostat, turning the star-forming furnace up and down. When star formation is too vigorous, the resulting supernova and Roman II regions heat and disperse the gas, slowing down the process. When things are too quiet, the gas has time to cool and condense, creating the conditions for a new burst of activity. This self-regulation is why a galaxy like our Milky Way only forms a few suns worth of stars each year, despite having billions of solar masses of gas in reserve. The feedback loop ensures that the galaxy's resources are used efficiently over billions of years, allowing for the long, stable periods necessary for the evolution of life on planets around stars like our own. This large-scale balancing act connects the life cycle of individual stars to the grand evolutionary story of their host galaxies, a theme we will return to as we explore even broader cosmic mysteries. Now, as we consider how feedback from massive stars can shape entire clusters, we encounter a class of cosmic object that defies easy categorization, existing in a kind of celestial no-man's land. These are brown dwarfs, and their very existence challenges our neat divisions between stars and planets. Imagine an object with the mass of a dozen or even 80 Jupiters. It's far too hefty to be considered a planet, yet it falls short of the critical threshold needed to ignite sustained hydrogen fusion in its core, the defining characteristic of a true star. These brown dwarfs are the universe's failed stars, glowing faintly with the residual heat of their gravitational birth, and the dull ember of deuterium fusion for a brief period, destined to cool and fade into darkness over billions of years. They occupy a strange twilight zone, and their population holds a peculiar clue that astronomers have dubbed the brown dwarf desert. This desert is not a physical place but a statistical anomaly. When astronomers search for companions to sun-like stars, objects orbiting a common center of gravity, they find a curious gap. There is a pronounced scarcity of brown dwarfs orbiting within a distance of about 3 to 5 astronomical units, which is roughly the region from the asteroid belt out to just beyond Jupiter in our own solar system. It's as if nature has a rule against placing these intermediate mass objects in close proximity to a star. We find plenty of planets, both gas giants and smaller rocky worlds, and we find stellar companions like small red dwarf stars at wider separations. But the close-in orbital real estate seems to be a veritable desert for brown dwarfs. This isn't just a minor curiosity. It's a glaring signpost suggesting that the formation mechanism for brown dwarfs is fundamentally different from the processes that build either planets or stars. So, what could create this desert? One compelling theory paints brown dwarfs as true failed stars. In this scenario, they form just like stars from the gravitational collapse of a small, isolated core within a molecular cloud. But the core they form from is simply too tiny, too anemic to gather the mass required to reach stardom. They are the stellar equivalent of a seed planted in poor soil, germinating but never reaching full bloom. If this is the primary method of formation, then the brown dwarf desert makes a certain kind of sense. In a binary star system, the two stars form from a single cloud that fragments into two large pieces. For a brown dwarf to be a close companion to a sun-like star via this method, the initial fragmentation would have to create one large piece and one very, very small piece, a pairing that might be inherently unstable or statistically rare, leading to the desert we observe. Another fascinating possibility is that many brown dwarfs start life not as failed stars, but as overachieving planets. In the competitive environment of a young planetary system, a planetary core might begin to accrete a massive gaseous envelope, aiming to become a gas giant. But what if the disk is particularly rich or the core forms very early? It could theoretically grow to brown dwarf proportions. However, if this happens, its immense gravity would strongly interact with the surrounding protoplanetary disk. This gravitational tussle could cause the budding brown dwarf to migrate inward, spiraling dangerously close to the central star. The desert, then, might exist because such a close-orbiting massive object is not stable over the long term. It could be ejected from the system entirely by gravitational interactions with the star or other planets, or it could even spiral all the way in and be consumed by the star. In this view, the brown dwarf desert is a dynamical graveyard, a region where such objects cannot survive, having either been flung into interstellar space or destroyed. This ejection idea is particularly compelling because it could also explain the existence of free-floating brown dwarfs, rogue objects wandering the galaxy unattached to any star. These lonely wanderers could be the refugees from such violent planetary system dynamics, cast adrift in their youth to cool alone in the galactic dark. The origin of brown dwarfs, therefore, remains a contentious and important puzzle. Are they primarily born like stars, or do they form like planets? The answer likely involves both pathways, with the observed desert being the key to understanding the relative importance of each. Solving this mystery is crucial because brown dwarfs represent a critical missing link, helping us understand the complete spectrum of objects that gravity can create, from the most massive stars to the smallest of planets, and refining our models for how solar systems, including our own, assemble themselves. As we explore the diverse outcomes of star formation, from the crowded clusters to the solitary brown dwarfs, we must now journey back in time to the very beginning, to a universe so alien and pristine that the rules of star birth were completely different. This brings us to a mystery that is not just about how stars form, but about how anything complex came to be at all. The enigma of the first stars, known to astronomers as population 3 stars. To understand them, we must erase everything we know about the cosmos today. Imagine a universe that is dark, profoundly dark, for hundreds of millions of years after the Big Bang. There are no galaxies, no planets, and no stars. The entire cosmos is a vast, expanding, and nearly uniform sea of hydrogen and helium gas, still warm from the primordial fireball. There is nothing else, no carbon, no oxygen, no iron, no silicon. Most critically, there is no dust. These first stars were born from a perfectly pure, pristine material, and this purity made them fundamentally unlike any star that has ever shone since. The absence of those heavier elements, which astronomers call metals, had a dramatic and counterintuitive effect on the star formation process. In a modern molecular cloud like the ones we see today, dust grains and complex molecules like carbon monoxide are absolutely essential. They act as a highly efficient cooling system. As a cloud collapses, the gravitational energy is converted into heat. If this heat isn't radiated away, the rising internal pressure would halt the collapse. Dust grains are brilliant at this. They glow in the infrared, efficiently carrying the heat away into space, allowing the cloud to continue contracting and fragmenting into smaller, denser cores. This efficient cooling is why we see stars forming in a wide range of masses, from tiny red dwarfs to massive blue giants. But in the early universe, there were no dust grains. The only coolant available was molecular hydrogen, a very weak and inefficient one. A cloud of pure hydrogen and helium could not cool down nearly as effectively. This meant that when the first gravitational instabilities finally arose in the primordial gas, the clouds had to be much more massive before their gravity could overcome the higher internal pressure from the heat. They could not fragment into small pieces. Instead, they collapsed as gigantic monolithic entities. This leads to the most startling prediction about population 3 stars, their sheer, unimaginable size. Theories and sophisticated computer simulations suggest that these first stars were not just large. They were behemoths, likely ranging from several dozen to several hundred times the mass of our Sun. Picture a star so colossal that it would make even the most massive stars in today's universe look diminutive. Their lives would have been as spectacular as they were brief. Fueled by such immense gravitational pressure in their cores, they would have burned their hydrogen fuel with a ferocious intensity, shining with the brightness of millions of suns and emitting copious amounts of ultraviolet radiation. A star hundreds of solar masses would live for only a few million years, a cosmic blink of an eye, before exhausting its nuclear fuel. Their deaths would have been equally extreme. Instead of a typical supernova, the most massive among them might have collapsed directly into black holes with little fanfare. Others would have died in pair instability supernova, explosions so violent and energetic that they would have completely obliterated the star, leaving no remnant behind and blasting newly forged heavy elements out into the void. This final act, this spectacular death, is why population 3 stars, though they are long gone, are so crucial to our own existence. They were the universe's first alchemists. In their fiery furnaces, through nuclear fusion, they cooked the first elements heavier than helium, carbon, oxygen, nitrogen, and a little iron. When they exploded, they seeded the pristine gas of the early universe with these first metals. This pollution was the key that unlocked the next chapter of cosmic evolution. Once even a tiny amount of these elements was mixed into the interstellar gas, everything changed. Dust grains could now form, and cooling became vastly more efficient. This allowed subsequent generations of gas clouds to fragment into much smaller cores, leading to the formation of lower mass, longer-lived stars like our Sun, and eventually the planets that orbit them. Every atom of oxygen you breathe and every atom of iron in your blood was forged in a star that died long ago. The first stars, the population 3 giants, provided the very first ingredients for that cosmic recycling program. The great challenge and the heart of this mystery is that we have never directly seen a population 3 star. They are purely theoretical constructs, ghosts from the dawn of time. Observing them is the holy grail of observational cosmology. The light from these stars is so faint and so redshifted by the expansion of the universe that it is far beyond the reach of even our most powerful current telescopes. Finding evidence for them is a primary goal for next-generation observatories like the James Webb Space Telescope and the planned extremely large telescopes on the ground. They will not look for the stars themselves, but for their indirect signatures, the chemical fingerprint they left on the gas clouds they illuminated, or the faint collective glow of their era, known as the cosmic dawn. Discovering and studying these first stars would complete our understanding of star formation, connecting the simple, monolithic collapse of the primordial universe to the rich, diverse, and self-regulating process we see today, a process that ultimately made our own world and us possible. Now that we've considered the colossal scale of the universe's first stars, it's time to turn our attention to the opposite end of the spectrum, to a question that defines the very lower limit of stardom itself. What is the smallest possible mass an object can have and still be considered a true star? This isn't just a matter of semantics, it's a fundamental physical boundary governed by the fierce and unforgiving laws of nuclear physics. The answer lies in achieving a specific and critical condition deep within an object's core. For hydrogen fusion, the stable, long-lasting process that powers stars like our Sun to ignite and sustain itself, the core must reach a staggering temperature of at least 10 million degrees Kelvin and an immense pressure. These extreme conditions are only possible if the object has enough mass. The gravitational crush from all that weight is what creates the incredible pressure and heat necessary to force hydrogen nuclei to overcome their mutual electrical repulsion and fuse together. This gravitational struggle sets a very specific lower limit, a cosmic minimum wage for stellar employment. This threshold is quantified at approximately 0.08 solar masses. That's about 80 times the mass of the planet Jupiter. An object that can muster this much mass will, after its contraction phase, successfully light the fusion furnace in its core and achieve a stable balance, earning the title of a main sequence star, specifically a small, cool red dwarf. But what happens if an object falls short? If a collapsing cloud core only gathers, say, 50 or 60 Jupiter masses of material, in that case it becomes a brown dwarf. The object will still contract under its own gravity, and it will even get incredibly hot, perhaps hot enough to briefly fuse a rare isotope of hydrogen called deuterium, or even lithium. But this is a fleeting fire. Deuterium is sparse, and once it's burned up, the fusion stops. Without the self-sustaining energy production of regular hydrogen fusion, the object cannot achieve long-term stability against gravity's pull. It will slowly radiate away its heat of formation over billions of years, fading from a faint red glow to near invisibility, a cold, dark ember in space. The line at 0.08 solar masses is therefore the great divider between stars that shine for trillions of years and failed stars that gradually dim into darkness. But is this minimum mass a universal constant, a fixed rule written into the fabric of physics that applies everywhere and always? This is where the mystery deepens considerably. The critical factor that sets this limit is the behavior of matter under extreme conditions, specifically the equation of state for hydrogen. This is a complex way of describing how hydrogen gas responds to being compressed, how its pressure and density relate as gravity squeezes it. In the modern universe, the presence of heavy elements and dust grains makes gas clouds very efficient at cooling. This efficient cooling allows a cloud to lose pressure support and contract further, making it easier to reach the high densities needed to ignite fusion even at relatively low masses. But what about in the early universe, which we just discussed, that was composed only of pure hydrogen and helium? Without those heavy elements to aid cooling, the primordial gas would have behaved differently. It would have resisted compression more effectively at lower densities. This leads to a fascinating possibility. The minimum mass for a population 3 star, a true first-generation star, might have been significantly higher than it is today. It's conceivable that in that pristine environment, an object would have needed to be even more massive to trigger fusion, perhaps pushing the boundary upward. The very definition of a star, therefore, might not be absolute but could depend on the chemical environment from which it is born. Understanding this boundary is absolutely essential for more than just classification. It's crucial for predicting the population of the smallest, most numerous objects in our galaxy. Red dwarfs are by far the most common type of star, and figuring out exactly how many there are and where the cutoff is between them and the even more numerous brown dwarfs helps astronomers model the total mass of our galaxy and understand how molecular clouds fragment. Every time we discover a star hovering right around this threshold, it provides a real-world test for our theories about stellar interiors and the physics of degenerate matter, the strange state where electrons are packed so tightly they themselves provide a pressure that halts gravitational collapse. It is this electron degeneracy pressure that ultimately puts a floor on the contraction of a brown dwarf, preventing it from shrinking further and differentiating it from a planet. So, in exploring how small a star can be, we are not just drawing a line in the sand. We are probing the fundamental interactions between gravity, pressure, and nuclear physics that govern the birth and life of every luminous object in the cosmos. Now, after considering the orderly boundaries that define a star's minimum mass, we encounter a class of celestial objects that defy such neat categorization by their very motion. Stars that are literally running away from home. Scattered across the galaxy, far from the bustling stellar clusters where they were born, are these stellar orphans known as runaway stars. They are cosmic speedsters, hurtling through space at velocities that can exceed hundreds of thousands of kilometers per hour, a pace that starkly contrasts with the more sedate drift of their neighbors. Their existence is not a quiet anomaly but a roaring testament to the incredibly violent gravitational dynamics that govern the dense environments of young star clusters. The story of how a star gets kicked out of its birthplace is a dramatic tale of cosmic billiards on an unimaginable scale. The most common scenario for creating these runaway stars involves the complex gravitational tango of binary star systems. Imagine 2 stars orbiting each other in a crowded cluster. Their peaceful dance can be violently interrupted when a third, more massive star passes uncomfortably close. The gravitational pull from this intruder can disrupt the delicate balance of the binary system. In a process known as the dynamical ejection scenario, the 3 stars engage in a frantic gravitational exchange. Often, the least massive member of the trio gets slingshotted away at high speed, like a stone from a sling, while the 2 more massive stars form a new, tighter binary system or are also sent careening in different directions. This gravitational slingshot effect can impart tremendous velocity to the ejected star, casting it out of the cluster entirely and onto a solitary path through the galaxy. It's a stellar version of survival of the fittest, where a close encounter literally determines a star's destiny. But there is an even more spectacular and devastating mechanism, the supernova ejection scenario. Consider a binary system where one star is significantly more massive than the other. Massive stars live fast and die young, and when the larger star exhausts its fuel, it ends its life in a cataclysmic supernova explosion. This explosion is so violent that it can instantly blow away a significant portion of the star's mass. If the stars were gravitationally bound, the sudden loss of this mass effectively cuts the cord tethering them together. The remaining companion, now freed from its orbital bond, is flung away at its original orbital velocity, continuing in a straight line like a ball released from a spinning tetherball. In some cases, if the supernova is slightly off-center, the explosion itself can give the surviving star an extra kick, a neutrino-powered push that sends it flying even faster. These runaway stars are the sole survivors of a catastrophic stellar divorce, carrying the memory of their partner's violent death in their swift motion. The paths of these runaway stars are more than just curiosities. They are valuable clues for cosmic archaeologists, because these stars retain the velocity they had when they were ejected. Astronomers can essentially trace their trajectories backwards through the galaxy. By carefully measuring a runaway star's current speed and direction, and modeling the gravitational forces it has experienced from the Milky Way's overall structure, scientists can project its path back in time millions of years. This reverse engineering often leads them right back to a specific star cluster or association, even if that cluster has since drifted apart and become difficult to identify. It's a powerful technique for piecing together the dynamical history of our galaxy, allowing us to identify ancient stellar nurseries that have long since faded from view and understand how gravitational interactions have shaped the stellar population we see today. The study of these stellar orphans provides a unique window into the frenetic and chaotic environment of a young star cluster, revealing a level of gravitational violence that is hidden from us once the cluster settles into a more sedate adulthood. Yet, while runaway stars tell a story of stellar families torn apart, the far more common narrative is one of togetherness. Look up at the sky, and many of the points of light you see are not single stars but pairs or even small groups locked in a gravitational dance. In fact, a significant fraction of all stars, perhaps even more than half, are born not as lonely individuals but as part of binary or multiple star systems. This simple fact forces us to reconsider the very picture of stellar birth. We've followed the journey of a single, collapsing core, but how does one cloud of gas and dust give rise to 2, 3, or even more stars orbiting each other? The answer lies in a process that turns a simple collapse into a cosmic act of division, where gravity itself becomes the architect of stellar families. The leading theory for this multiplication is a concept known as fragmentation. Imagine a single, large molecular cloud core beginning its inevitable inward collapse. As it shrinks, it spins faster, just as we've discussed. But if this core has even a slight irregularity in its shape or density, or if it contains pockets of turbulence, the collapse will not be perfectly smooth. The core can become unstable, wobbling and deforming as it contracts. In particular, as it flattens into a rotating disk-like structure, it can become susceptible to what's called gravitational instability. Think of it like a spinning blob of pizza dough. As you spin it, it naturally flattens, but if you spin it fast enough or if the dough is uneven, it can tear apart, splitting into two smaller blobs. In a similar way, a rotating cloud core can fragment, pinching off a separate, self-gravitating clump of gas that will then collapse on its own to form a second star. This new star and the original one remain bound by gravity, becoming a binary system. Alternatively, fragmentation can occur a bit later in the process within the accretion disk itself. A massive, dense disk surrounding a young protostar can also become gravitationally unstable, forming spiral arms that can condense into additional stellar companions. This is a powerful mechanism for creating triple or even quadruple star systems, all originating from a single, fertile cloud. However, while the basic idea of fragmentation is sound, the devil is in the details, and those details present a major challenge for astrophysicists. Sophisticated computer simulations can create binary stars from a collapsing cloud, but getting the models to perfectly match the rich diversity we observe in the real universe is extraordinarily difficult. For instance, why do we see such a wide range of separations between binary stars? Some pairs orbit so closely they nearly touch, completing a revolution in just days, while others are separated by distances greater than our entire solar system, taking thousands of years to complete a single orbit. The initial conditions of the cloud, its exact amount of rotation, its magnetic field strength, its internal turbulence seem to finely tune the final architecture of the system. Furthermore, the distribution of mass between the stars is another puzzle. Do they tend to be twins with nearly equal masses, or is one star consistently more massive than its companion? Reproducing the observed statistics of these mass ratios and orbital separations is a key test for our theories, and it tells us that we are still missing some of the finer points of the physics involved, particularly how the stars continue to interact and accrete gas after they have initially formed. The prevalence of these stellar partnerships is far from a mere curiosity. It has profound and sweeping implications for everything that follows. For planet formation, a binary system presents a dramatically different and more chaotic environment. The gravitational pull of a second star can severely disrupt the protoplanetary disk, truncating it, warping it, or making it impossible for planets to form in stable orbits at all. In some cases, planets can form, but they may end up in wide, looping orbits around both stars, creating the iconic Tatooine-like worlds from science fiction. In other, more chaotic systems, a planet could be violently ejected into interstellar space, becoming a rogue planet. The presence of a companion star also directly affects the evolution of the stars themselves. In a close binary system, if one star evolves faster and expands into a giant, it can begin to transfer mass onto its companion. This can lead to spectacular events like nova explosions, or, if the star is massive enough, even trigger a supernova. In the most extreme cases, the binary system can end its life as a pair of orbiting neutron stars or black holes, their slow in-spiral destined to end in a cataclysmic merger that ripples space-time itself with gravitational waves. The simple act of a cloud fragmenting into a binary system, therefore, sets the stage for some of the most energetic and transformative events in the cosmos, linking the quiet beginnings of star formation to the most violent endings the universe has to offer. But beyond the grand ballet of gravity and turbulence within the cold, dark hearts of these molecular clouds, another, more subtle drama is unfolding, a story written not in forces but in molecules. We have journeyed through the physics of collapse, but now we must delve into the chemistry of creation. The frigid interiors of these stellar nurseries are far from empty. They are vast, cosmic laboratories, teeming with a surprising diversity of chemical compounds. Astronomers, using powerful radio telescopes, have identified hundreds of different molecules in these regions, from simple hydrogen gas to astonishingly complex organic molecules like ethanol, the alcohol in beverages, and even glycine, the simplest amino acid, a fundamental building block of life. This discovery transforms our view of these clouds from simple collections of gas and dust into intricate chemical factories, setting the stage not just for stars, but for the potential of biology itself. The key to this rich chemistry lies in the unique environment of the cloud. The extreme cold, just a few tens of degrees above absolute zero, and the pervasive darkness are not hindrances but essential ingredients. In the warmth and light of interstellar space, high-energy ultraviolet radiation from stars would quickly break apart these delicate molecules. But deep inside a dense cloud, the outer layers of gas and dust act as a protective shield, blocking this destructive radiation and creating a sanctuary where chemistry can thrive. In this frigid quiet, something remarkable happens. individual atoms and simple molecules drifting slowly can meet and stick to the surfaces of microscopic dust grains. These tiny grains act as cosmic catalysts, providing a solid surface where chemical reactions can occur much more efficiently than in the sparse gas alone. It is on these frigid, dusty workbenches that simple molecules like carbon monoxide and water ice can slowly, over millions of years, assemble into the complex organic compounds that astonish us. However, this delicate chemical balance is entirely dependent on the environment, and as soon as a protostar begins to form, everything changes. The birth of a star is an act of cosmic arson, dramatically altering the chemistry of its surroundings. As the protostar heats up, it begins to radiate warmth, creating a thermal front that moves outward through the cloud. This heat has a profound effect on the ices that have been accumulating on the dust grains for eons. Molecules that have been frozen in place for millions of years are suddenly given enough energy to sublimate, to jump directly from a solid ice back into a gaseous state. This process creates what astronomers call a hot core or hot corino around the young star, a region rich with complex molecules now liberated from their icy prisons and floating freely in the gas. The specific temperature at which different molecules sublimate creates a chemical clock and a map. By measuring the molecular composition of the gas around a protostar, we can effectively measure its temperature and age, reading the history of the heating process. This astrochemistry is far from a mere academic curiosity. It plays a direct and crucial role in the physics of star formation itself. Remember the problem of cooling. For a cloud to collapse, it must radiate away the heat generated by its own gravitational contraction. Those complex molecules we've been discussing are brilliant at this. As they spin and vibrate, they emit radiation at very specific wavelengths, primarily in the radio and microwave parts of the spectrum. This molecular line radiation is an incredibly efficient cooling mechanism. A cloud rich in molecules like carbon monoxide can cool itself down much faster than a cloud of pure hydrogen and helium. This efficient cooling allows the cloud to lose pressure support, condense further, and fragment into the smaller cores that will become individual stars. So, the chemistry of the cloud directly controls its ability to give birth to stars in the first place, creating a feedback loop where chemistry enables physics, which in turn alters the chemistry. The implications of this chemical history extend all the way to the formation of planets and the potential for life. The protoplanetary disk that forms around the young star inherits this complex inventory of molecules. The location of various molecules within the disk is determined by temperature. Water, for example, freezes out at what is known as the snowline, a specific distance from the star where temperatures are low enough for water ice to form. Inside this line, water is a gas. Outside it, it freezes onto dust grains, dramatically increasing the amount of solid material available to build planetary cores. This simple chemical transition likely played a key role in our own solar system, allowing giant planets like Jupiter to form beyond the snowline where there was more solid material to work with. Furthermore, the complex organic molecules forged in the initial molecular cloud and later cooked in the protoplanetary disk are delivered to the surfaces of forming planets by comets and asteroids. The chemistry of star formation, therefore, is not an isolated process. It is the first step in a chain that may lead to the prebiotic conditions necessary for life, meaning the ingredients for biology are being woven into the fabric of planetary systems from the very moment their parent star begins to shine. And so, as we marvel at the complex chemistry unfolding within these cosmic clouds, we must turn our attention to the humble, microscopic agents that make it all possible. It's easy to be captivated by the grand forces of gravity and magnetism, or the brilliant fury of young stars. But the true unsung heroes of this entire cosmic drama are the smallest participants of all, interstellar dust grains. To call them mere dust is a profound understatement. These are not the simple specks you find on a shelf. They are complex, microscopic minerals and ices, some no larger than a few hundred atoms across, forged in the atmospheres of ancient stars and scattered into space by stellar winds and supernova explosions. Yet, despite their minuscule size, their collective impact on star formation is nothing short of monumental, acting as the essential facilitators without which the birth of new suns would be far less efficient, if not impossible. The first and perhaps most vital role these tiny grains play is that of a cosmic cooling system. As a molecular cloud begins to collapse under its own weight, a fundamental problem arises. The gravitational energy released by the infalling gas is converted into heat, causing the cloud's internal temperature to rise. This creates an outward pressure that fights against the inward pull of gravity. If this heat isn't removed, the rising pressure will eventually halt the collapse, leaving the cloud in a state of frustrated equilibrium. This is where dust grains become the star formation process's greatest ally. These microscopic particles are incredibly efficient at absorbing this thermal energy and then re-radiating it away as infrared light. Think of them as billions of tiny radiators, or a sophisticated air conditioning system for the entire cloud. By glowing faintly in the infrared, they carry the heat away into the coldness of space, allowing the cloud to continue contracting and condensing. Without this efficient cooling mechanism, the cloud would struggle to reach the high densities necessary to form stars, especially lower mass stars like our Sun. The very ability of a cloud to fragment into multiple, dense cores is directly dependent on how effectively its dust grains can cool it down. Beyond their role as cosmic coolants, dust grains serve as essential protective shields. The interstellar medium is flooded with harsh, high-energy ultraviolet radiation from nearby stars. This radiation is a destructive force, capable of breaking apart the delicate molecules that are so crucial for cooling and chemistry. However, the outer layers of a dense molecular cloud are packed with dust grains that act as a formidable line of defense. They absorb and scatter this damaging ultraviolet light, creating a dark, quiet sanctuary within the cloud's interior. It is only in this shielded environment that fragile molecules like molecular hydrogen can survive, and that more complex organic molecules can slowly, patiently assemble on the grain's surfaces. This protective shadow is what allows the rich chemical factory we discussed earlier to operate, turning the cloud's core into a reservoir of the very materials that might one day become part of planetary systems. This leads us to their third critical function. Dust grains are the universe's ultimate chemical laboratories. The vast, empty space within a cloud makes it incredibly unlikely for two atoms or simple molecules to meet and react. They are simply too far apart. But on the surface of a dust grain, everything changes. These grains provide a solid anchor, a meeting place where atoms can stick, migrate, and eventually bond with one another. In the deep freeze of the cloud, ices of water, carbon monoxide, ammonia, and methane build up in layers on these tiny surfaces. When a stray hydrogen atom drifts by and lands on this icy mantle, it can tunnel through the ice, eventually finding a partner to form molecular hydrogen, the primary fuel for stars. But the chemistry goes far beyond simple hydrogen. The constant, gentle irradiation from cosmic rays and the warmth from occasional shock waves can provide enough energy to trigger more complex reactions on these grain surfaces, creating the precursors to life itself, such as formaldehyde and even simple sugars. The dust grain, in this sense, is not a passive spectator but an active participant in building the chemical complexity that will be inherited by new stars and their planets. The importance of these grains is so profound that their fundamental properties, their size, composition, and abundance directly shape the outcome of star formation across cosmic time. In the early universe, before generations of stars had lived and died to seed space with dust, the first molecular clouds were pristine, containing only hydrogen and helium. Without dust grains to provide efficient cooling, these clouds could not fragment easily, likely leading to the formation of only monstrously large stars, as we discussed with Population 3. But as those first stars exploded, they polluted the cosmos with the first heavy elements, which condensed into the first dust grains. With each subsequent generation of stars, the universe became dustier. This means that star formation has evolved over the lifetime of the cosmos. Modern molecular clouds, enriched with a wide variety of silicate and carbonaceous grains, can cool and fragment much more efficiently, leading to the birth of a full spectrum of stars, from small red dwarfs to massive blue giants. The tiny dust grain, therefore, is not just a player in star formation. It is a key driver of galactic evolution, its increasing abundance over billions of years making the universe a more fertile place for the creation of diverse stellar systems, including those that might harbor life. This fundamental barrier, the simple fact that stardust is born within a shroud of its own making, presents one of the most practical and persistent challenges in all of astronomy. If you were to point even the most powerful optical telescope, like the Hubble Space Telescope, toward a nearby stellar nursery, you would see invisible light, a scene of profound darkness. The Orion Nebula, for instance, appears to the naked eye as a faint, wispy smudge, but Hubble reveals it as a spectacular, glowing cloud. However, that glorious view is only the surface. The brightest stars in the trapezium cluster are blasting away the gas and dust immediately around them, creating a glowing cavity. But behind that brilliant facade, deeper within the cloud, the true birthing grounds are hidden by an impenetrable wall of dust, completely opaque to the light our eyes are designed to see. It's like trying to observe the heart of a storm cloud from the outside. You see the dark, turbulent surface, but the intricate dynamics within are utterly concealed. This is the observational challenge. Star formation happens in the darkest of cosmic closets, and to open the door, we cannot rely on the key of visible light. To solve this puzzle of perception, astronomers have become masters of the entire electromagnetic spectrum, learning to see the universe in colors invisible to human eyes. Each type of light, from the long, gentle waves of radio to the short, piercing bursts of X-rays, serves as a unique key that can unlock a different part of the story. The first and most crucial key is infrared light. Think of a dusty cloud on a cold night. While it blocks the light from a distant street lamp, the dust itself, having absorbed a little warmth, will glow with a faint heat-like radiation. This is precisely what happens in space. The dust grains, warmed by the embedded protostars, emit light in the infrared part of the spectrum. Telescopes like the Spitzer Space Telescope and now the revolutionary James Webb Space Telescope are specifically designed to detect this infrared glow. JWST, with its massive gold-coated mirrors and sensitive instruments, acts as a powerful heat vision camera for the cosmos. It can peer straight through the vast clouds of dust, revealing the warm, embedded protostars within, showing us the newborn stars while they are still swaddled in their dusty blankets. This gives us an unprecedented view of the earliest stages of stellar gestation, from the first collapse of a core to the intricate structures of protoplanetary disks, all by sensing the heat signature of the hidden activity. But seeing the warm dust and the young stars is only half the picture. To understand the environment from which they form, we need to map the cold, raw material itself, the molecular gas. This is where radio astronomy comes into play. Giant radio telescopes like the Atacama Large Millimeter Array, or ALMA, located high in the Chilean desert, are tuned to detect the much longer wavelengths of radio waves. Cold molecular gas does not glow brightly on its own, but it does possess a unique fingerprint. Molecules like carbon monoxide, hydrogen cyanide, and even complex organic compounds are constantly spinning and vibrating, and as they do, they emit radiation at very specific, precise frequencies in the radio and sub-millimeter bands. ALMA dozens of precise antennas work together as a single, gigantic eye, allowing it to map the distribution and motion of this cold gas with stunning detail. It can trace the intricate filamentary structure of a molecular cloud, measure the supersonic motions of turbulent gas, and even observe the subtle rotation of a collapsing core. While JWST shows us the babies and their warm cribs, ALMA shows us the architecture of the maternity ward itself, the flows of material that feed the entire process. Then there is the high-energy side of the story, which requires a completely different set of tools. Young stars, especially during their tempestuous Tauri phase, are incredibly violent. Their surfaces are racked by colossal flares and intense magnetic activity that heats the stellar atmosphere to millions of degrees. Gas at such extreme temperatures emits copious amounts of X-rays. Observatories like NASA Chandra X-ray Observatory are designed to detect this high-energy radiation. While X-rays cannot penetrate the thick dust of a natal cloud, they are brilliant for studying young stellar objects that have partially emerged from their cocoons. By observing these X-rays, astronomers can measure the strength of a young star's magnetic field, study the powerful flares that can profoundly impact surrounding protoplanetary disks, and even census the stellar population of a young cluster, distinguishing the truly young stars from older, background stars that might be mixed in. Each observational window, infrared, radio, and X-ray, provides a distinct and essential piece of the puzzle. The ultimate challenge, however, is not just collecting this multi-wavelength data, but weaving it together into a single, coherent narrative. It is a significant technical and interpretive endeavor. An image from JWST might show a beautiful, glowing protostar. An ALMA map might reveal a complex network of gas filaments feeding that same object. And a Chandra observation might show a point of intense X-rays right at the protostar's location. Combining these datasets requires meticulous alignment and a deep understanding of the physics each wavelength represents. It's like trying to understand an elephant by having one person describe its smooth, curved tusks, another its rough, leathery skin, and a third the sound of its trumpet. Only by synthesizing all these different senses can you form a complete picture of the animal. In the same way, astronomers must be synthesists, using the infrared view to understand the thermal structure, the radio data to understand the kinematics of the gas, and the X-ray data to understand the stellar activity, merging them all within the framework of physical theory to truly comprehend the dynamic, violent, and beautiful process of a star being born. This puzzle of perception is a constant reminder that our understanding of the cosmos is limited only by the cleverness of our methods and our ability to see the universe in all its many shades of light. After witnessing the dramatic bursts of creation within stellar nurseries, it might seem natural to assume that our galaxy is a constant hive of star-forming activity. But when we step back and measure the Milky Way's total output, a surprising truth emerges. On average, across the entire vast expanse of our galaxy, the rate of star formation is remarkably, almost puzzlingly, slow. Each year, the combined efforts of all its molecular clouds produce only a handful of new stars, amounting to just a few times the mass of our Sun. Given the staggering reservoirs of cold gas available, enough to form billions of stars, this feels incredibly inefficient. It's as if a factory with limitless raw materials has decided to operate at a leisurely, almost cautious pace. This leads us to a mystery of galactic proportions. Why is the star formation rate so modest? The answer is not that the universe is lazy, but rather that it is governed by a sophisticated system of checks and balances, a cosmic regulatory mechanism that prevents gravity from turning all that gas into stars in a single, frantic burst. This regulation is the work of three powerful forces we've already met, now acting on a galaxy-wide scale. First, there is the inherent turbulence within the giant molecular clouds themselves. Remember that chaotic, supersonic motion. On a local level, it creates the dense seeds for stars, but on a grand scale, it acts as a supporting pressure that holds the cloud up against its own weight. This turbulent energy keeps large swaths of gas from collapsing all at once, effectively rationing the cloud's material over millions of years. Then, woven through that turbulent gas are the magnetic fields. These invisible lines of force provide an additional form of support, creating a magnetic cushion that resists compression. The slow process of ambipolar diffusion, where neutral particles slip past the magnetic anchors, acts as a throttle, ensuring that collapse proceeds at a measured, controlled rate rather than a free fall. These two factors alone would significantly slow things down, but the most powerful regulator of all is stellar feedback. Feedback is the game changer. The moment the first massive stars are born, they immediately begin to influence their own birthplaces. Their intense ultraviolet radiation heats and ionizes the surrounding gas, creating expanding bubbles of hot plasma that can disperse the very cloud that created them. Then, a few million years later, the most massive of these stars explode as supernova. These cataclysmic events inject a staggering amount of energy back into the interstellar medium, violently shaking the galaxy's gas reservoir. This feedback has a dual personality. Locally, it can compress gas and trigger new star formation, but globally, it is a profoundly disruptive force. It heats the diffused gas, making it harder for it to cool and condense into new clouds, and it can blast apart existing molecular clouds before they have a chance to convert more than a small fraction of their mass into stars. This self-regulation is the key to the slow and steady rate we observe. Without it, a galaxy would rapidly convert its gas into stars in a brief, brilliant starburst, burning through its fuel supply in a cosmic frenzy, and then fading into a quiet, red and dead retirement. The consequence of this delicate balancing act extends far beyond a simple number. It fundamentally determines a galaxy's destiny and its very appearance. The equilibrium between gravity and these opposing forces dictates a galaxy's evolutionary path. A galaxy where gravity has the upper hand, perhaps because it has a particularly rich gas supply or has experienced a merger that compressed its gas, will undergo a rapid starburst phase. We see this in brilliant, irregular galaxies and in the dense cores of merging galaxies, where star formation rates can be hundreds of times higher than in our Milky Way. Conversely, a galaxy where feedback dominates, where supernova and stellar winds have effectively heated and dispersed most of the cool gas, will see its star formation decline and eventually cease. This is the fate of large, elliptical galaxies, which are often composed of old, red stars and contain very little cool gas for future generations. Our own Milky Way exists in a kind of golden mean, a stable, sustained equilibrium. It has enough gas to continue forming stars for billions of years, but the regulatory forces of turbulence, magnetism, and feedback are strong enough to ensure that this process is a marathon, not a sprint. This long, slow timeline is in fact a prerequisite for the development of life as we know it. It allows for the gradual enrichment of the interstellar medium with heavy elements from successive generations of stars, and it provides the long-term stability necessary for planetary systems like our own to form and evolve. The seemingly slow pace of star formation is not a sign of cosmic inefficiency, but rather the signature of a mature, self-regulating system, one that carefully manages its resources to ensure a long and productive life, fostering the conditions where suns and their worlds can arise. But this careful, measured pace of star formation we see in our own Milky Way is not the only way a galaxy can live. For some galaxies, star birth is not a gentle simmer but a roaring, all-consuming firestorm. These are the starburst galaxies, cosmic maelstroms where the normal rules are thrown out the window and creation goes into spectacular overdrive. In these extreme environments, the star formation rate doesn't just tick upward slightly. It explodes, reaching a pace that can be hundreds, even 1,000 times greater than that of a typical spiral galaxy. Where our galaxy might form 1 or 2 sun-like stars each year, a starburst galaxy can churn out dozens. This isn't just a quantitative difference, it's a qualitative shift into an entirely different mode of galactic existence, a feverish state that reveals the raw, untamed power of gravitational collapse when it is pushed to its absolute limits. The trigger for this cosmic conflagration is almost always one of the most violent events in the universe, a galactic collision or a very close encounter. When 2 galaxies, each containing billions of stars and vast reservoirs of gas, drift too close together, their mutual gravitational pull begins a slow-motion dance of destruction and creation. The stars themselves rarely collide, the spaces between them are far too vast, but the immense clouds of interstellar gas and dust within each galaxy feel the pull profoundly. As the galaxies intertwine, their gravitational tides stretch, squeeze, and slam these gas clouds together with incredible force. Imagine taking 2 handfuls of fine, fluffy snow and smashing them together. The result isn't 2 separate handfuls, it's a single, dense, compressed snowball. On a galactic scale, this process forces huge quantities of gas into a relatively small volume, dramatically increasing its density and overwhelming the regulatory forces that usually keep star formation in check. The turbulence and magnetic support that act as brakes in a quiet cloud are utterly swamped by the sheer, compressive power of the collision. Gravity wins in a landslide, and the gas responds by collapsing en masse, igniting a firestorm of star birth that can light up an entire galaxy. We can see the aftermath of these collisions in stunning detail. The antennae galaxies, for instance, are a classic example of 2 spiral galaxies caught in a violent merger. In telescopic images, they look less like pristine pinwheels and more like a cosmic car wreck, with long, streaming tails of stars flung out into space by gravitational tides. But the most spectacular activity is happening in the overlapping central regions. There, the compressed gas glows with the fierce pinkish light of countless newly formed H-II regions, vast bubbles of hydrogen ionized by the ultraviolet radiation from massive newborn stars. The entire area is a sprawling, chaotic stellar nursery, a factory operating at maximum capacity. Another famous starburst galaxy, Messier 82, is often called the cigar galaxy for its elongated shape. Its core is a powerhouse, a central region so densely packed with young, hot stars and supernova remnants that it outshines the rest of the galaxy combined. A superwind of material, driven by the combined effect of stellar winds and supernova explosions. is even blasting out of the galaxy's core perpendicular to its disk, a visible testament to the incredible energy being released by this frenzy of creation. These starburst galaxies are more than just spectacular sights. They are invaluable cosmic laboratories. They allow us to study star formation under conditions of extreme pressure and density that we could never replicate on Earth or even simulate perfectly in our computers. By observing them, we can test the limits of our theories. How does the initial mass function change when stars form in such a crowded, violent environment? Do we get a higher proportion of massive stars? How do protoplanetary disks survive, or do they get destroyed in the intense radiation field of a starburst? These galaxies present a natural experiment on a grand scale, showing us what happens when the cosmic thermostat of feedback is temporarily broken. The feedback is still there. In fact, it's more intense than ever, but it's overwhelmed by the sheer scale of the collapse. This helps us calibrate our models for more quiescent environments like our own. By understanding star formation at its most extreme, we gain a deeper appreciation for the subtle balances that govern it in more peaceful settings. Furthermore, starburst galaxies offer us a direct window into the universe's past. In the early cosmos, galaxies were much closer together, and collisions and mergers were far more common events. The universe was a more crowded, violent, and dynamic place. It's likely that a significant fraction of all the stars we see today in giant elliptical galaxies were formed during intense starburst episodes triggered by galactic mergers billions of years ago. So, when we look at a starburst galaxy in our local universe, we are essentially looking back in time, witnessing a mode of star formation that was once the norm rather than the exception. This allows us to piece together the evolutionary history of galaxies, understanding how the majestic, stable spirals and the quiet, red ellipticals of today were shaped by the fiery bursts of their youth. The starburst phenomenon, therefore, connects the present-day universe with its tumultuous origins, revealing a key chapter in the story of how galaxies grow and evolve across cosmic time. Now consider the legacy that a star's birth spin leaves behind, a legacy that echoes for billions of years. The rotation rate of a young star is not just a fleeting characteristic. It is a fundamental parameter that sets the stage for its entire life story, influencing everything from its magnetic personality to its potential for hosting habitable worlds. A star that spins rapidly will generate a much stronger magnetic field through the dynamo action in its convective zone. This, in turn, fuels a more intense stellar wind, a relentless stream of charged particles flowing outward from the star. For any planets orbiting such an active star, this can be a hostile environment. A fierce stellar wind can erode or even strip away a planet's atmosphere over time, especially if that planet is close in. Furthermore, a strong magnetic field leads to more frequent and powerful flares, sudden, violent releases of energy that can bathe nearby planets in harmful X-ray and ultraviolet radiation, posing a significant challenge for the emergence and survival of life. Conversely, a slow rotator like our Sun, with its comparatively gentle magnetic activity and milder wind, provides a far more stable and nurturing environment, allowing planetary atmospheres to persist and chemical reactions to proceed undisturbed for eons. The initial spin, therefore, is a critical factor in defining a star's habitable zone, not just in terms of distance, but in terms of the overall space weather conditions. But what determines this crucial starting speed? The initial rotation rate is the final outcome of a complex tug-of-war over angular momentum that takes place during the star's formation. As we've seen, the collapsing cloud core brings with it a tiny amount of rotation, which is then amplified dramatically as the core shrinks. The central mystery is how much of this built-up spin is shed before the star reaches the main sequence. The leading actor in this breaking process is the accretion disk. Think of the disk as a cosmic flywheel and a brake system combined. As material spirals inward through the disk to be accreted by the star, it carries angular momentum with it. However, the process is not straightforward. Magnetic fields, which are frozen into the ionized gas of the inner disk, can act as a lever. They connect the rapidly rotating central star to the slower moving outer regions of the disk. This connection allows the star to effectively transfer some of its rotational energy outward, slowing its own spin while speeding up the outer disk. The duration of the star's accretion phase is therefore crucial. A star that is fed by a long-lived disk for millions of years has a prolonged period during which this magnetic braking can operate, likely resulting in a slower initial rotation. On the other hand, a star whose disk is dispersed early, perhaps by the intense radiation of a massive sibling in a cluster, might have this braking mechanism cut short, leaving it spinning much faster as it begins its independent life. Measuring this initial spin, however, presents a formidable observational challenge. For a very young star that is still deeply embedded in its natal envelope and accreting vigorously, its surface is obscured and its light is variable, making precise rotation measurements incredibly difficult. Astronomers must rely on indirect methods or wait until the star has cleared its surroundings and settled into the Tauri phase. Even then, there is a complicating factor. The star's strong magnetic fields can create large starspots that, as they rotate in and out of view, cause changes in the star's brightness. By tracking these brightness variations, we can determine the star's rotation period. What these observations reveal is a wide spread of rotation rates among young stars of the same mass and age. Some Tauri stars rotate quite slowly, completing a turn in over a week, while others whirl around in just a day or two. This diversity is a direct clue, telling us that the processes governing angular momentum lost during formation are not uniform. They must be sensitive to subtle differences in initial conditions, such as the strength of the magnetic field, the mass of the disk, or the dynamic history of the stellar nursery. Unraveling the mystery of the initial rotation rate is therefore key to understanding the rotational evolution of all stars. Why do stars of the same mass and age exhibit such a range of spins later in life? It likely all traces back to the circumstances of their birth. The distribution of spins we see in young clusters is the primordial starting grid for a long race that lasts billions of years, a race where stars gradually slow down as they lose angular momentum through their magnetized winds. By studying this initial distribution and linking it to other properties like the presence or absence of disks, we can begin to piece together a more complete picture of those critical early moments. This knowledge helps us build better models for how stars like our Sun evolve, and it provides essential context for interpreting the vast population of exoplanets we are discovering. The spin of a star at birth is a hidden variable with profound consequences, a single number that encapsulates the complex history of its formation and casts a long shadow over the future of its potential planetary system. But after the grand-scale drama of galactic starbursts and the star's own rotational legacy, we must now shrink our perspective down to the most intimate scale imaginable, to the very dust motes dancing within the protoplanetary disk. This is where the story of planet formation truly begins, not with a bang, but with a whisper-soft touch. The disk surrounding a young star is a swirling maelstrom of gas and microscopic dust grains, the same particles that acted as cosmic coolants and chemical factories within the molecular cloud. For planets to ever come into being, these tiny, separate specks must somehow find a way to clump together. to grow from microscopic fragments into massive worlds. This transition from disorganized dust to structured solid bodies is one of the most delicate and poorly understood phases in all of astrophysics, a critical bridge that must be crossed, yet one that seems fraught with peril at every step. The first stage of this growth seems deceptively simple. In the cold, calm outer regions of the disk, dust grains are coated in a layer of ice, making them slightly sticky. When these frosty particles gently collide, they don't bounce apart. Instead, they cling together, forming fragile, fractal-like aggregates that resemble cosmic snowflakes. This is the process of coagulation, and it can fairly quickly build particles up to sizes of a few centimeters. But here, the first major obstacle appears. As these pebbles grow, they begin to interact with the gas in the disk in a new and dangerous way. The disk is not a perfect vacuum. It's filled with gas that is orbiting the star at a speed set by its own pressure balance. Due to this pressure, the gas actually orbits a tiny bit slower than the solid particles. The pebbles, feeling a headwind from this slower moving gas, begin to lose orbital energy. Like a bicyclist pedaling into a strong wind, they slow down. And when an object in orbit slows down, its orbit decays. This creates a phenomenon known as radial drift, a relentless inward spiral that drags these precious planetary building blocks toward the hungry central star before they have a chance to grow any further. The timescale for this drift is alarmingly short. A meter-sized boulder orbiting at the distance of the Earth from the Sun could be pulled into the star in just a few hundred years. This is the meter-size barrier, a theoretical death sentence for growing solids, threatening to vacuum up the raw materials of planets before they can ever coalesce. But if radial drift is so efficient, how do any planets form at all? Clearly, nature has found a way to overcome this barrier, and one of the most promising solutions involves a collective effort. Instead of thinking of solids growing in isolation, imagine them as a population. As pebbles drift inward from the colder outer disk, they can encounter regions where the pressure changes, creating a kind of traffic jam. One particularly effective trap is the water snowline, the distance from the star where temperatures are low enough for water vapor to freeze into ice. Inside this line, water is a gas, outside it's solid. This transition creates a sharp pressure bump in the disk, and just like leaves accumulating against a grate, drifting pebbles can get caught and concentrated there. In these high-density traps, the rate of collisions skyrockets. Instead of gentle, sticking collisions, the particles now collide with enough energy to compact themselves into denser, more robust objects. More importantly, when the density of solids becomes high enough, their collective gravitational influence can begin to take over. This is the gateway to the next, even more mysterious stage, the formation of planetesimals. The jump from a loose swarm of pebbles to a solid, kilometer-sized planetesimal is the true great leap forward in planet formation, and it represents a major unsolved problem. How do you go from a collection of smaller rocks to a single, massive body? One leading theory is gravitational instability. If the pebbles become sufficiently concentrated in a small region of the disk, their combined gravity can overcome the turbulent forces trying to pull them apart. The entire cloud of pebbles could undergo a rapid collapse, directly forming a planetesimal tens or even hundreds of kilometers across in a surprisingly short time. This would be a top-down process where the large object forms almost instantly from a crowd of smaller ones. The other main theory is continued collisional growth, a bottom-up approach. In this scenario, a few lucky pebbles manage to avoid destruction and slowly, painstakingly accumulate more mass through countless collisions, eventually reaching a size where their own gravity becomes strong enough to pull in other pebbles, a stage known as Runaway Accretion. The challenge with this slow and steady model is that collisions between larger objects are more likely to be destructive, shattering the growing body back into fragments rather than building it up. The initial conditions set during this critical phase of dust and pebble evolution are absolutely paramount, as they dictate the entire future architecture of the planetary system. The efficiency of pebble trapping, the location of pressure bumps, and the mechanism of planetesimal formation will determine where the building blocks of planets originate. This, in turn, influences the types of planets that form. A system with strong, early pebble concentration might quickly build giant planet cores in the outer disk, while a system where growth is slower and more difficult might only produce smaller, rocky worlds closer to the star. The chemical composition of the dust grains inherited from the molecular cloud is also locked into these planetesimals, determining the ultimate chemistry of the planets they will become. The seemingly humble process of dust sticking together is therefore the foundational act of world building, a delicate dance that must navigate a gauntlet of physical challenges to lay the groundwork for the diverse and wondrous planetary systems we observe throughout the galaxy. Now, as we've seen how the slow, patient process of core accretion might struggle to build giant planets before the gas disappears, we must confront a radical alternative, a theory that suggests nature has a far more dramatic and swift method for creating these cosmic giants. This is the mystery of the disk instability model, a concept that turns the conventional step-by-step story of planet formation on its head. Instead of building a giant planet from the bottom up, like assembling a skyscraper brick by brick, disk instability proposes a top-down approach where a planet can be born almost instantaneously from a large-scale gravitational collapse within the protoplanetary disk itself. It's the difference between carefully baking a cake layer by layer and having the entire cake suddenly materialize out of the batter due to a powerful, spontaneous transformation. The entire scenario hinges on a specific and extreme condition. The disk must be exceptionally massive and very cold. Imagine a protoplanetary disk that contains a significant fraction of the central star's own mass, and whose outer regions are frigid enough to allow gravity to overcome the internal pressure of the gas. In this situation, the entire disk can become gravitationally unstable. It's akin to a vast, spinning fluid becoming so heavy that it can no longer maintain a smooth, stable flow. This instability manifests as spiral arms of dense gas, much like the spiral arms of a galaxy winding through the disk. Within these arms, the density can skyrocket. If a pocket of gas becomes dense enough, its own self-gravity can overwhelm any supporting pressure and cause it to collapse directly into a clump. This clump, containing many times the mass of Jupiter from the very beginning, would then rapidly contract under its own weight, quickly forming a giant planet without ever needing a solid core to start the process. It's a gravitational shortcut, a way to leapfrog over the slow and perilous stages of dust coagulation and planetesimal accretion. The most compelling argument for disk instability is its breathtaking speed. While the core accretion model might take several million years to build a gas giant, a significant portion of the disk's short lifetime, a planet born via disk instability, could form in a mere few thousand years, a virtual instant on the cosmic timescale. This rapid formation elegantly solves the problem of how to capture a massive gaseous atmosphere before the protoplanetary disk dissipates. It's a particularly attractive explanation for the existence of gas giant planets orbiting very far from their host stars at distances of hundreds of astronomical units. In the core accretion model, it's difficult to form a planet so far out because the material is sparse and the orbital timescales are incredibly long, making the slow process of core growth practically impossible. But if the disk is massive enough to be unstable at such great distances, a planet could condense right where we see it, in situ, without having to migrate from a birthplace closer to the star. However, the disk instability model is not without its own significant challenges. The primary hurdle is whether the conditions necessary for instability are common or even realistic. For a disk to become unstable, it needs to be both extremely massive and very cool. While massive disks certainly exist, especially around young stars, whether they are massive enough to trigger this global instability is a matter of intense debate. Furthermore, even if a clump does form, it is not guaranteed to survive. The violent environment of a young disk is filled with turbulence and heated by the star's radiation. A nascent gas clump could be torn apart by tidal forces or simply heat up and redisperse before it can fully collapse into a stable planet. Simulations show that for a clump to survive, the cooling time of the gas must be very short, allowing the clump to radiate away its heat and contract quickly before it falls apart. Whether real protoplanetary disks can cool this efficiently in their outer regions is a key unanswered question. The great scientific quest, therefore, is not to prove one theory right and the other wrong, but to determine under what circumstances each mechanism dominates. It is entirely plausible that our universe uses both methods. Core accretion might be the primary pathway for forming gas giants like Jupiter and Saturn within the warmer, denser inner regions of disks where solid material is plentiful. Meanwhile, disk instability could be the favored mechanism in the cold, massive outer disks, creating the bizarre worlds we've discovered on wide orbits. The diversity of exoplanetary systems we see, from hot Jupiters scorchingly close to their stars to solitary giants drifting in the deep freeze far away, suggests that planet formation is not a one-size-fits-all process. The existence of a planet like HR 2562b, a massive world orbiting its star at a distance about 20 times farther than Pluto is from our Sun, is a prime candidate for having formed via disk instability. Finding and studying more such systems, especially with next-generation telescopes like the James Webb Space Telescope, will allow us to measure the atmospheric composition of these distant giants. A key prediction of the disk instability model is that planets formed this way should have atmospheres that reflect the composition of the primordial disk gas, rich in hydrogen and helium, unlike planets formed by core accretion, which might show evidence of enrichment from solid material. By reading these chemical fingerprints, we may finally be able to distinguish the birth story of individual planets, revealing whether they were the product of a slow, meticulous construction or a sudden, gravitational flash of inspiration. This fleeting existence of the protoplanetary disk introduces a race against time of cosmic proportions. Imagine the disk as a vast reservoir of planetary potential, a swirling sea of gas and dust orbiting a young star. Yet, astronomical observations deliver a startling verdict. This fertile ground is not a permanent feature. On average, these gas-rich disks dissipate, vanishing into the void within a remarkably short window of just a few million years. To put that in perspective, it is less than 1,000th of the current age of our own solar system. This creates an unforgiving deadline for the formation of planets, especially for the gas giants like Jupiter and Saturn. These colossal worlds are not predominantly made of rock and metal. Their immense bulk comes from massive, thick atmospheres of hydrogen and helium captured directly from the disk. To become a gas giant, a planet must first form a solid core massive enough to exert a strong gravitational pull, and then it must rapidly gobble up a tremendous volume of gas from its surroundings, all before the star's radiation and winds blow that gaseous buffet away. The lifespan of the disk is therefore the ultimate timer, the great regulator that determines which stars will host giant planets and which will be surrounded only by smaller, rocky worlds. The mechanisms behind this rapid dispersal are a fascinating interplay of destructive forces, each acting like a different hand erasing the disk. The first and most straightforward process is simple accretion. The disk, after all, is the star's leftover food. Throughout its youth, the star continues to dine on the inner regions of the disk, drawing material down magnetic field lines onto its surface. This ongoing feast slowly depletes the disk from the inside out. While accretion is a steady drain, it is often not fast enough to account for the observed rapid disappearance of the entire disk. This is where a more aggressive process takes center stage, photoevaporation, as the young star, now in its active Tauri phase, unleashes intense ultraviolet radiation. This high-energy light bathes the disk. The UV photons are like tiny hammers, striking the gas molecules in the disk's upper layers and heating them to extreme temperatures. This heat gives the molecules enough energy to escape the star's gravity altogether, creating a slow but steady wind that boils the disk away from the top down. It's as if the star is using its own light to systematically dismantle the very structure that gave it birth. This effect is particularly potent in the inner disk, close to the star where the radiation is strongest and can effectively create a gap that expands outward over time. A third, and still somewhat mysterious, actor in this drama is the possibility of magnetically driven winds. Similar to the powerful bipolar jets launched during the earliest protostellar phase, but gentler and broader, these winds could flow outward from the surface of the disk itself. Powered by the interaction between the disk's rotation and its magnetic fields, these winds could carry away mass and angular momentum, contributing to the disk's depletion. The relative importance of these three mechanisms, accretion, photoevaporation, and winds, can vary from system to system. In a quiet, isolated star, photoevaporation might be the dominant eraser. But if a star is born in a dense cluster, the situation becomes even more extreme. The intense ultraviolet radiation from nearby massive, hot stars can cause external photoevaporation, a far more violent process that strips away the outer disk like a cosmic sandblaster, dramatically shortening its lifespan even further. The consequences of this dispersal timeline are written in the final architecture of every planetary system we see. The exact timing and manner of the gas removal act as a powerful sculptor. For instance, if the gas disappears very quickly within just 1 or 2 million years, it slams the door shut on the formation of gas giants. There simply isn't enough time for a large core to form and accrete its massive atmosphere. This might explain why many stars seem to host only Neptune-sized worlds or rocky planets. The window of opportunity for gas giant formation closed before the process could complete. Conversely, if the disk persists for a longer period, perhaps 4 to 5 million years, it allows ample time for giant planets to form in the colder outer regions. But the story doesn't end there. The process of photoevaporation, which eats away at the disk from the inside, can have a profound effect on planets that have already formed. As the inner disk is eroded, it can alter the orbits of planets, potentially driving them inward in a final act of migration, or leaving them stranded at specific orbital distances. The presence or absence of a gap carved by photoevaporation might determine whether a Jupiter-like planet migrates all the way in to become a hot Jupiter or remains in a wider, cooler orbit. The fleeting lifespan of the protoplanetary disk is therefore not just a countdown clock. It is a dynamic and active participant in shaping the final planetary system. its dispersal mechanisms carving the orbits and determining the types of worlds that will remain to circle the star for billions of years to come. But if we imagine planets forming in neat, orderly rings around their star, like our own solar system might suggest, the discovery of thousands of exoplanets has delivered a shocking revelation. That picture is almost certainly wrong. The architecture of many planetary systems is chaotic, with gas giants scorchingly close to their stars and other planets in wildly eccentric orbits. This bizarre arrangement points to a universal phenomenon that reshapes young solar systems, a planetary migration. The idea that planets can move vast distances from their birthplaces is a revolutionary shift in our understanding, revealing that a solar system's youth is a dynamic and often violent period of rearrangement. Far from being fixed in place from the moment they coalesce, young planets are like pieces on a cosmic chessboard, pushed and pulled by powerful forces within the gaseous disk that still surrounds them. This grand movement comes in two primary forms, each dictated by the size of the planet and its relationship to the disk. The first, known as Type I migration, affects smaller, Earth-sized or Neptune-sized planets that are not massive enough to carve a deep gap in the disk. These worlds, while substantial, are still at the mercy of the gas flow. As such a planet orbits, it creates spiral waves of density in the surrounding gas, much like a boat creates waves in water. The gravitational interaction between the planet and these waves is incredibly complex. In most disk models, the wave that leads the planet tends to pull it forward, while the wave that trails behind pulls it backward. Due to the delicate balance of pressure and temperature in the disk, the leading wave often exerts a stronger pull. This net effect acts as a drag, causing the planet to lose orbital energy and slowly, inexorably, spiral inward toward the star. This process can be alarmingly fast. A young Earth-like planet could be dragged from a comfortable, habitable zone orbit into a fiery doom in the star in just 1 million years, a mere instant in astronomical time. For larger planets, the story changes dramatically, leading to Type II migration. When a planet grows to be a true giant, something remarkable happens. Its gravitational influence becomes so powerful that it can clear a distinct annular gap in the protoplanetary disk, like a snowplow clearing a path. This gap effectively isolates the planet from the rest of the disk. At this point, the planet's motion becomes locked to the evolution of the disk itself. The entire disk is slowly draining onto the star, and as it does so, the planet, trapped in its gap, is carried along with the flow like a leaf caught in a river current. This type of migration is generally slower than Type I, but it can still move a Jupiter-mass planet over enormous distances. The direction is typically inward, but under certain conditions, such as interactions with other planets or specific pressure gradients in the disk, it can even be directed outward. The sheer scale of this migration is staggering. A gas giant could form in the cold, icy outer regions of a system, where solid material is plentiful for building a core, and then migrate all the way inward to become a hot Jupiter, a class of planet we see frequently, but whose existence was completely unexpected before the era of exoplanet discovery. The obvious and terrifying question then becomes, if migration is so efficient, why doesn't every planet fall into its star? Why does our solar system, for instance, have giant planets in stable orbits far from the Sun? This is where the mystery of stopping mechanisms becomes absolutely critical. Nature must have built-in brakes to halt this destructive spiral. One of the most promising ideas involves the very dissipation of the disk that we just discussed. As the protoplanetary disk is evaporated by the star's radiation, its inner regions disappear first. A planet migrating inward might find itself reaching the inner edge of the disk, where the gas density drops to virtually zero. At this boundary, the gravitational torques that were driving the migration suddenly vanish. The planet is left stranded, its inward journey abruptly halted, forever frozen at an orbital distance that bears no relation to its birthplace. Another powerful stopping mechanism is gravitational resonance. If multiple planets are migrating at different rates, they can become captured in a gravitational resonance where their orbital periods form a simple integer ratio. This lock creates a stable configuration where the planets gravitationally shepherd each other, preventing further large-scale migration. The intricate orbital resonances observed in Jupiter's moons and in the Kuiper belt objects beyond Neptune are likely fossils of such a process. The early history of our own solar system provides compelling, though indirect, evidence that we too experienced a significant migration event. The most successful model for explaining the structure of our outer solar system is the Grand Tack hypothesis. This theory proposes that a young Jupiter first migrated inward through the disk, carving a path toward the Sun. Before it could get too close, however, Saturn formed and began its own inward migration. Saturn caught up to Jupiter, and the two giants became locked in a special orbital resonance. This gravitational partnership reversed their migration direction, causing them to tack back outward, like a sailboat changing course against the wind. This grand journey inward and then back outward would have dramatically sculpted the inner solar system, scattering planetesimals and influencing the formation and composition of Mars, Earth, and Venus. The very arrangement of our planetary family, and perhaps the delivery of water to Earth, may be a direct consequence of this dynamic and migratory youth. Understanding migration is therefore not just about explaining bizarre exoplanets. It is the key to unlocking our own origins and appreciating that the stable orbits we take for granted today are the peaceful aftermath of a far more chaotic and mobile past. Now we come to a factor that acts as a cosmic fingerprint, a chemical signature imprinted on every star that tells the story of its ancestry and profoundly influences the worlds it can create. This is the concept of metallicity, a term astronomers use not for the presence of metallic elements alone, but as a shorthand for the total abundance of all elements heavier than hydrogen and helium. When a star forms, its atmosphere acts as a pristine sample of the composition of the molecular cloud from which it was born. A star's metallicity is therefore a direct relic, a chemical fossil preserving the conditions of its birth environment. This single measurement, often expressed as the ratio of iron to hydrogen compared to the Sun's ratio, turns out to be one of the most powerful predictors of planetary architecture. The discovery of this correlation was a landmark moment in exoplanet science, revealing that the universe has a preferred recipe for building certain kinds of solar systems, and that recipe depends heavily on the available ingredients. The most striking and well-established relationship is the clear correlation between high stellar metallicity and the presence of gas giant planets. Stars like our Sun, which are relatively metal-rich, are far more likely to host Jupiter-sized or larger worlds than stars that are metal-poor. The logic behind this is beautifully straightforward and ties directly into the core accretion model of planet formation. To build a gas giant, you must first construct a solid core massive enough, roughly 10 times the mass of Earth, to have the gravitational pull necessary to rapidly accrete a huge envelope of hydrogen and helium gas from the protoplanetary disk. If the initial cloud was rich in heavy elements, meaning it was full of dust grains made of silicates, carbon, and ices, then there is simply more solid, building block material available in the disk. This abundance makes it easier and faster for planetary embryos to collide and grow, allowing them to reach that critical core mass before the short-lived protoplanetary disk dissipates. In a metal-poor environment, the disk is anemic in dust, the solids are scarce, and the process of core growth is like trying to build a snowman during a light flurry. It's a slow, difficult struggle that might never reach a critical size. The giant planet, needing a hearty meal of gas, arrives at the table too late to find the buffet still open. However, when we shift our focus from gas giants to smaller, rocky worlds like our own Earth, the story becomes significantly murkier and far more intriguing. The relationship between stellar metallicity and the occurrence of terrestrial planets is much less clear. Some studies suggest there might be a weak correlation, but it is nowhere near as strong as it is for giant planets. This makes a certain intuitive sense. While a Jupiter-mass planet contains the equivalent of over 300 Earths of material, a rocky planet like ours is, by comparison, a modest construction project. It requires far less solid material to form. A protoplanetary disk, even one around a star with relatively low metallicity, might still contain enough dust to cobble together a few Earth-mass worlds. The formation of rocky planets might be a more universal process, less sensitive to the initial chemical wealth of the cloud. This opens up a thrilling possibility that small, rocky planets could be common around a wide variety of stars, including older, metal-poor stars that formed early in the galaxy's history. The potential for Earth-like worlds, therefore, might be spread much more widely across the cosmos than the potential for Jupiter-like giants. This distinction forces us to consider the broader galactic environment. Our Sun, with its moderate metallicity, was born in a relatively rich region of the Milky Way that had been seeded with heavy elements by generations of previous stars. But what about stars forming in different corners of the galaxy, or in different types of galaxies altogether? A star born in the galactic halo, where the gas is primordial and metal-poor, will have a protoplanetary disk with a completely different inventory of materials. Not only would the total amount of dust be lower, but the specific chemical ratios might be different, potentially affecting the mineralogy of any terrestrial planets that form. Conversely, a star forming in the dense, metal-rich environment near the galactic center might have a disk so thick with dust that planet formation proceeds with explosive efficiency, perhaps producing an overabundance of giant planets or rocky worlds so large they become super-Earths. By studying star and planet formation across this entire spectrum of galactic environments, we move beyond just cataloging exoplanets and begin to understand the fundamental, universal physics that govern their birth. We can ask whether the processes of core accretion and disk instability are universal laws or if they are modulated by the chemical environment. This research helps us distinguish between conditions that are local to our cosmic neighborhood and those that apply throughout the universe. Ultimately, the mystery of metallicity is central to the grandest question of all: are we alone? Understanding how the chemistry of a birth cloud influences the outcome of planet formation is a critical step in assessing the likelihood of finding another Earth. It tells us where to focus our search. If rocky planets can form around stars with a wide range of metallicities, then our list of potentially habitable stellar targets grows enormously. But the story may be even more nuanced than simply the presence of a planet. The specific metallicity of the star might also influence the composition of the resulting planets. A world forming from metal-rich material might have a different internal structure, a different volcanic activity, and a different abundance of elements crucial for life, such as phosphorus or carbon, compared to a world born from more pristine stuff. The iron core of our planet, the silicate mantle, and the presence of water could all be indirect consequences of the specific metallicity of the cloud that collapsed to form our Sun. So, when we measure the metallicity of a distant star, we are not just gauging its potential to host planets. We are reading the ingredient list for the entire planetary system, an inventory that may ultimately determine whether that system can nurture the delicate chemistry of life. While we often picture star formation as a grand battle between gravity and pressure, there is another, far more subtle force at work, an invisible rain of energy that permeates every corner of the galaxy. Journeying from the deepest voids of space, these are cosmic rays, not rays of light, but a relentless hail of atomic nuclei, mostly protons, accelerated to nearly the speed of light by some of the universe's most violent events. Their origins are as dramatic as their energy, born in the shock waves of supernova explosions, unleashed from the environs of black holes, or perhaps even accelerated by the fierce winds of massive stars. These tiny, hyper-fast projectiles are everywhere, silently passing through our bodies, through the Earth, and crucially, through the cold, dark hearts of the molecular clouds where stars are born. Within those quiet, dusty nurseries, they play a surprisingly vital role, acting as the unseen electrical engineers of the star formation process. The key to their influence lies in a process called ionization. A molecular cloud is composed mostly of neutral hydrogen gas, atoms minding their own business, with their positively charged protons neatly balanced by their negatively charged electrons. This neutral gas is largely oblivious to magnetic fields, but when a high-energy cosmic ray comes screaming through, it can smash into a neutral hydrogen atom with enough force to knock an electron loose. This act of ionization creates a free electron and a positively charged hydrogen ion or proton. This might seem like a minor event, but its consequences are profound. By creating a population of charged particles, however sparse, the cosmic rays provide a crucial link between the gas and the magnetic fields that are woven through the cloud. The magnetic field, which before could only push against the gas as a whole, can now grab onto these individual charged particles. The ions and electrons become trapped, forced to spiral along the magnetic field lines, while the vast majority of neutral particles continue their own path. This difference in motion is the very essence of ambipolar diffusion, the slow, steady process that allows neutral gas to seep through the magnetic scaffolding and condense into a dense core. Without cosmic rays providing this initial, low level of ionization, the magnetic fields would be permanently locked into the gas, creating a state of perfect support that could prevent gravitational collapse from ever beginning. Cosmic rays, therefore, are the unsung heroes that weaken the magnetic grip just enough to allow gravity to start its work. This introduces a fascinating possibility that the rate of star formation across our galaxy might not be uniform. What if the flux of cosmic rays raining down on a particular molecular cloud is stronger or weaker? In regions of the galaxy buzzing with recent supernova activity, like the spiral arms, the cosmic ray flux would be intense. This would lead to a higher level of ionization within the local clouds. A higher ionization rate means the magnetic field is more strongly coupled to the gas. This could, somewhat counterintuitively, actually strengthen the magnetic support against gravity, potentially slowing down the process of ambipolar diffusion and putting the brakes on star formation. It's as if the very explosions that trigger star formation by compressing gas also produce a secondary effect that can regulate its pace. Conversely, in a quieter, more isolated region of the galaxy, far from the stellar fireworks, the cosmic ray flux would be much weaker. There, ionization would be lower, the magnetic fields would be less tightly coupled, and neutral gas might collapse more freely and rapidly. This subtle variation in an invisible particle flux could be a hidden dial, fine-tuning the efficiency of star birth from one galactic neighborhood to the next, creating pockets of vigorous starburst activity and other areas of relative quiet. Detecting and measuring this influence is a tremendous challenge, as it requires piecing together clues from across the electromagnetic spectrum and even beyond. Astronomers can map the gamma-ray glow produced when cosmic rays interact with the gas in molecular clouds, giving them an indirect measure of the cosmic ray density. By comparing this with observations of how quickly stars are forming in different clouds, we can begin to test these ideas. It's a detective story that connects the death throes of massive stars to the birth cries of new ones, a cycle of cosmic feedback operating on a microscopic scale. These energetic particles, often overlooked in the grand narrative of cosmic creation, are a perfect example of how the universe is interconnected. The same cataclysmic explosions that scatter the heavy elements of life also generate an invisible rain that helps govern the very formation of the next generation of stars and planets, weaving a subtle thread between stellar death and stellar rebirth. But for every star that finds a stable home within a cluster and every planet that settles into a neat orbit, there is a casualty of this chaotic gravitational environment. The formation of a solar system is not a perfectly efficient assembly line. It is a messy, often violent process that produces a significant amount of cosmic debris and, even more strikingly, complete outcasts. Simulations of dense star clusters reveal a startling truth. Gravitational interactions are so fierce that they can literally fling newborn planets and even failed stars out of their birth systems, condemning them to an eternal journey through the dark, cold interstellar void. These are the unbound objects, the rogues and orphans of the galaxy, and their existence forces us to completely rethink the definition of a planetary system. The primary mechanism for creating these exiles is a gravitational slingshot, a dramatic event that typically involves a young planetary system undergoing a close encounter with a passing star. Imagine a nascent solar system with its giant planets still settling into their orbits. If another star wanders too close, its gravitational pull can violently disrupt the delicate balance. In a frantic gravitational exchange, the least massive object in the system, often a Jupiter-sized planet or a small brown dwarf, can be ejected at a speed that exceeds the escape velocity of the entire cluster. It's a cosmic game of billiards on an unimaginable scale, where the cue ball is a star and the planets are sent scattering. In some cases, the entire planetary system can be destabilized, with multiple worlds being flung out in different directions, or one planet being ejected while the others are thrown into wildly eccentric orbits. This process highlights the inherent danger of a crowded stellar nursery. What might have been a potential Earth-like world in a stable orbit could instead become a dark, frozen wanderer, lost to the interstellar deep. Detecting these rogue planets is one of the greatest challenges in modern astronomy. Unlike stars, they emit very little light of their own. A Jovian mass rogue planet, after billions of years of cooling, would only glow faintly in the infrared. A smaller, Earth-sized rogue would be completely dark, visible only if it passed directly in front of a background star, briefly magnifying its light through a phenomenon called gravitational microlensing. These microlensing events are incredibly rare and unpredictable, like trying to spot a specific firefly blinking once in a vast, dark field from thousands of miles away. Despite the difficulty, surveys have begun to find them. Astronomers have detected a population of free-floating planetary mass objects, some with masses as low as a few times that of Earth, drifting alone through our galactic neighborhood. Their discovery confirms that our theories of dynamical ejection are correct, and that the galaxy is teeming with these invisible wanderers. The predicted number of these rogue planets is staggering. Some estimates suggest there could be billions, even trillions of them roaming the Milky Way, vastly outnumbering the stars themselves. This revelation completely changes our perspective on the output of star formation. It means that for every successful, stable solar system like our own, there could be several failed systems, or systems that lost members to the gravitational chaos of their youth. Studying this population provides a crucial census of a stellar nursery's total productivity, including its dark, unseen output. By counting these rogues, we can better understand the efficiency of planet formation. How much material that initially collapses in a cloud actually ends up in stable orbits? The answer appears to be not all of it. A significant fraction of the planetary mass budget is effectively lost to intergalactic space. The existence of these lonely worlds also sparks profound questions about the nature of planets and habitability. Could a rogue planet ever host life? It seems a bleak prospect. Without a sun, its surface would be frozen solid, a perpetual nightscape with temperatures near absolute zero. However, there is a speculative possibility. A large rogue planet with a thick hydrogen atmosphere could trap enough internal heat from its radioactive decay to maintain a subsurface ocean of liquid water, much like Jupiter's moon Europa. In such a scenario, life could potentially exist around hydrothermal vents on the ocean floor, completely isolated from any star, fueled solely by the planet's internal geochemistry. While this is a fascinating thought, it underscores the extreme and lonely fate of these objects' potential abodes of life that are forever cut off from the light of any sun, drifting through the eternal darkness between the stars. Their discovery reminds us that star formation is a prolific but wasteful process, creating not just the familiar lights in our sky, but also a vast, invisible population of dark, wandering worlds. Now, as we consider the dynamic migrations of young planets, we must also recognize that the protoplanetary disk is not a uniform environment. It is a place of distinct chemical zones, marked by boundaries as fundamental as any continent on Earth, yet defined not by geography but by temperature. The most important of these frontiers is the snow line, a subtle but powerful transition that acts as a cosmic sorting mechanism for the building blocks of planets. Imagine a line encircling the young star, a specific distance where the ambient temperature drops to a critical value around 170 Kelvin, or roughly 100 degrees below 0 Celsius. Inside this boundary, the fierce heat from the star ensures that volatile compounds like water, ammonia, and methane exist as vapors, but cross this invisible threshold and the environment becomes a deep freeze. At these frigid temperatures, these molecules can no longer remain as gas. They flash freeze directly onto the surfaces of the ubiquitous dust grains, coating them in a thick layer of ice. This transition from gas to solid might sound simple, but its consequences for planet formation are absolutely transformative. The snowline creates a dramatic shift in the available building materials. Inside the snowline, the solid material is composed primarily of refractory substances, dust made of silicates and metals, which can withstand the heat. But outside the snowline, the dust grains suddenly become much larger and more abundant, now encased in a thick mantle of ice. This icy coating significantly increases the total amount of solid material in the disk. More importantly, these icy grains are far more sticky. When they collide, they are much more likely to clump together rather than shatter or bounce apart. This is the great leap forward for planet formation. Beyond the snowline, the process of building larger bodies from microscopic dust becomes exponentially easier and faster. The region just outside this boundary becomes a veritable construction zone, where the rapid coagulation of icy particles can quickly form the kilometer-sized planetesimals that are the essential seeds for planetary cores. It is widely believed that this is why our own solar system's gas giants, Jupiter and Saturn, formed in the outer regions. The snowline provided the perfect environment for their massive, icy rocky cores to assemble with incredible speed, allowing them to gravitationally capture vast amounts of hydrogen and helium gas before the protoplanetary disk dissipated. However, the snowline is not a static, permanent fence. It is a dynamic boundary that evolves with the young star system. As the star ages, its luminosity changes. In its earliest, most luminous phases, the snowline might be located quite far out, perhaps beyond the orbit of Jupiter. But as the star settles onto the main sequence and its brightness stabilizes, the snowline will migrate inward. Furthermore, the very process of accretion can heat the inner disk, temporarily pushing the snowline even further outward. This movement has profound implications. A planetesimal that forms beyond the snowline could later find itself inside it as the boundary shifts inward. When this happens, the icy mantle that gave it a growth advantage begins to sublimate, turning back into vapor. The object loses its sticky surface and its growth may stall. This dynamic evolution of the snowline can therefore create a complex tapestry of planetary compositions. It might explain the existence of asteroids with puzzlingly different compositions, or even contribute to the delivery of water to the inner planets. If icy bodies formed in the outer disk are scattered inward by the gravity of growing giants, they could ferry water across the snowline, eventually impacting and hydrating young, rocky worlds like Earth. The moving snowline is not just a boundary in space, but a timeline of chemical change that is written into the very structure of every planetary system. But to truly grasp the significance of this cosmic connection, we must see it in action. Picture a young, fiery Tauri star, its surface raging with magnetic storms and powerful flares. This intense activity isn't contained. It blasts the surrounding protoplanetary disk with a hurricane of ultraviolet radiation and a relentless stellar wind. This assault has a direct and dramatic impact on the planet-forming material. Close to the star, the fierce heat can prevent volatile compounds from condensing onto dust grains, effectively creating a dry zone where only refractory materials like rock and metal can survive. This stellar fury also drives a process called photoevaporation, where the disk's gas is heated to the point of escaping the star's gravity, slowly boiling away the very raw materials needed to form gas giant planets. The star, in its tempestuous youth, is actively sculpting the architecture of its future solar system, potentially determining whether it will birth gas giants or only small, rocky worlds, and setting the inner boundary beyond which planets cannot form. Simultaneously, the process of planet formation itself is sending feedback signals that directly influence the star. The primary channel for this is the accretion of material. As pebbles, planetesimals, and gas spiral inward through the disk onto the star's surface, they deliver not just mass but also angular momentum. This ongoing feast can have a profound effect on the star's rotation. If the accretion flow is steady and channeled along magnetic field lines, it can act as a brake, slowing the star's spin. However, if the accretion is lumpy and episodic, perhaps caused by a growing planet clearing a gap in the disk, it can lead to violent bursts of mass transfer that might actually spin the star up. The chemical composition of the accreting material matters too. If a growing Jupiter-like planet has already hoovered up most of the heavy elements in the inner disk, the gas later falling onto the star might be chemically impoverished, potentially leaving a measurable signature in the star's atmosphere. The planets as they form are literally helping to write their parent star's life story, influencing its spin, its chemical makeup, and its magnetic personality. This inseparable relationship forces a complete overhaul of our observational strategies. In the past, astronomers might have studied a young stellar object to understand the star, and then separately observed its disk to understand planet formation. We now know this is an artificial division. To decode the history of a system like our own, we must observe it as a single, integrated unit. When the James Webb Space Telescope peers at a young star, it doesn't just see a point of light and a separate disk. It sees a complex system where the star's radiation is heating the inner disk rim, where gaps and spirals in the disk signal the presence of unseen planets, and where the chemistry of the disk is being altered by both the star's light and the gravitational influence of the nascent worlds. Each observation is a snapshot of a continuous, dynamic conversation. The properties of the star explain the structure of the disk, and the features of the disk reveal the processes shaping the star. This holistic view is the only path to understanding why our solar system looks the way it does, and why the thousands of other planetary systems we've discovered exhibit such an astonishing and beautiful diversity. The link between star and planet formation is the final, crucial piece of the puzzle, revealing that the birth of a sun and the genesis of its worlds are two acts of a single, magnificent cosmic play. For centuries, our only blueprint for a planetary system was the one we call home, a collection of rocky worlds orbiting close to the sun, with a neat asteroid belt separating them from a distant realm of gas giants. This orderly, familiar arrangement seemed like a logical, perhaps even inevitable, outcome of the formation process. But then we started looking at other stars, and that comforting model was completely upended. The discovery of thousands of exoplanets has revealed a cosmos of almost bewildering variety, a menagerie of worlds and system architectures that defy our solar system's example at nearly every turn. We found hot Jupiters, gas giants larger than our own Jupiter, but orbiting so close to their stars that their years are shorter than an Earth week, their atmospheres scorched to unimaginable temperatures. We discovered systems with multiple planets larger than Earth but smaller than Neptune, so-called super-Earths or mini-Neptunes, crammed into orbits smaller than Mercury's, a configuration completely absent from our own solar system. We even found planets in resonant chains where the orbital periods of neighboring worlds form perfect ratios, creating a delicate gravitational harmony. This astonishing diversity was not predicted by the simplistic models based solely on our own cosmic backyard. Instead of a single, universal blueprint, the universe has shown itself to be a master of improvisation, constantly experimenting with different designs. This incredible variety is not a sign of chaos, but rather the direct and logical outcome of the complex star and planet formation processes we've been exploring. Each planetary system is a unique experiment, a cosmic fingerprint whose final architecture is imprinted by a cascade of events stretching back to the initial conditions of the parent molecular cloud. Think of it like baking. The final cake depends on the specific recipe, the mixing process, and the baking time. In this cosmic kitchen, the recipe is the chemical composition and mass of the cloud. A cloud rich in metals will have more solid material for building planetary cores, potentially leading to a system with gas giants. The mixing process is the turbulent, dynamic environment of the stellar cluster where the star was born. Was it a quiet, isolated birth, or a violent, crowded one where gravitational encounters could have truncated disks or ejected planets? And the baking time is the lifespan of the protoplanetary disk itself. Did it dissipate quickly, halting the growth of gas giants, or did it persist long enough for planets to form and then migrate vast distances? The specific combination of these factors, and many others, Like the strength of the magnetic fields and the efficiency of pebble accretion determines whether a system will end up looking like our own, like a tightly packed family of super-Earths, or like a star with a lonely hot Jupiter. This diversity, while initially a challenge to our theories, has become our most valuable guide. It forces us to move beyond a one-size-fits-all model and to appreciate the full spectrum of physical processes at play. The existence of hot Jupiters, for instance, was the single biggest clue that planetary migration is not just a theoretical idea but a powerful and common reality. Before their discovery, the idea that a planet could move from its birthplace was a niche concept. Now it is a cornerstone of planet formation theory. Similarly, the prevalence of super-Earth suggests that the process of building planets somewhere between Earth and Neptune in size is a very common and efficient outcome, one that for some reason did not occur in our own system, perhaps because Jupiter's early migration cleared out that orbital real estate. Each bizarre new system we discover is like a new data point on a vast graph, helping us to refine our models and understand which processes are dominant under which conditions. Ultimately, this grand tapestry of planetary systems teaches us a profound lesson about our place in the cosmos. Our solar system is not the standard model. It is simply one possible outcome, one particular experiment that yielded a specific and perhaps somewhat unusual result. This realization elevates the study of star and planet formation from a quest to understand our own origins to a much broader inquiry into the universal principles that govern the birth of worlds. The incredible variety we see is a direct reflection of the richness and complexity of the physical laws that shape gas and dust into stars and planets. It tells us that the universe is far more creative and diverse than we ever imagined, and that the potential for different kinds of worlds and perhaps different kinds of life is correspondingly vast. Having journeyed through the intricate physics of how individual stars are born, we now must lift our gaze to the grandest scale imaginable, to the fate of star formation across the entire cosmos. The story we have been telling is not a perpetual one. Astonishingly, the universe is in the process of shutting down its stellar production lines. We live in what astronomers call the stelliferous era, the age of stars, but this era has a beginning, a peak, and an inevitable end. Observations from powerful telescopes like Hubble have painted a clear and dramatic history. The universe's star-forming heyday was roughly 10 billion years ago. At that cosmic noon, galaxies were churning out new suns at a ferocious pace, a rate perhaps 10 or 20 times higher than what we see in the universe today. Since that peak, there has been a long, slow, and steady decline. The great fires of creation are gradually burning themselves out. The reasons for this cosmic dimming are fundamental and, in a way, deeply sobering. Primary fuel for star formation is cold, neutral hydrogen gas. Galaxies are not closed systems. They are constantly using up this fuel to make stars. While some gas is recycled when stars die, especially from lower mass stars that gently shed their outer layers, a significant portion becomes locked away. When a massive star explodes as a supernova, much of its enriched material is blasted out into the hot, diffuse intergalactic medium, where it is too energetic to easily cool and collapse again. Even more permanently, when a low-mass star like our Sun dies, it leaves behind a white dwarf, a dense Earth-sized ember that will slowly cool over trillions of years, its material effectively removed from the cosmic cycle of star birth. Furthermore, when the largest stars collapse into black holes, their mass is essentially sequestered from the universe of light. This is a one-way street. The universe is gradually converting its usable star-forming fuel into forms that are inaccessible. Compounding this fuel shortage is the expansion of the universe itself. As space stretches, the distances between galaxies increase. This means that fresh, pristine gas from the intergalactic medium has a harder time falling into galaxies to replenish their dwindling reservoirs. Galaxies are becoming more and more isolated, forced to live on their existing gas supplies like a town cut off from its supply routes, slowly consuming its remaining stores. At the same time, this expansion causes the cosmic background radiation, the leftover heat from the Big Bang, to cool further. While this cooling might seem like it would help gas condense, it is offset by the fact that the gas reservoirs themselves are becoming more diffuse and harder to gather. The overall trend is one of winding down. Based on our current understanding, the future is a long, slow fade. The largest, most massive stars, which live for only a few million years, will be the first to disappear from the scene, their explosive deaths no longer lighting up galactic nurseries. Then, over hundreds of billions of years, the rate of formation for Sun-like stars will trickle to a halt. Galaxies will become dominated by long-lived, faint red dwarfs, stars so frugal with their hydrogen fuel that they can shine for trillions of years. The universe will grow progressively darker and redder, but is this bleak, dark future the final word? Or could there be a reboot, a new cycle of creation billions of years from now? This question pushes us to the very limits of cosmology and into the realm of profound speculation. Our current models point toward the heat death, or big freeze scenario, where the universe continues expanding forever, becoming increasingly cold, dark, and dilute. In this view, star formation does indeed cease entirely. The last red dwarfs will eventually consume their fuel, fading to black dwarfs' cold, dark stellar remnants. The universe will be populated by these dead stars, along with neutron stars and black holes, drifting apart in an ever-cooling emptiness. However, our understanding is incomplete. The nature of dark energy, the mysterious force driving the accelerated expansion of the universe, is the greatest wild card. If the properties of dark energy were to change in the far future, it could theoretically lead to a big rip, tearing all structures apart, or perhaps even a big crunch, where the expansion reverses and the universe collapses back on itself. A big crunch could potentially recycle all matter and energy in a final, fiery collapse, perhaps seeding a new Big Bang and a new stelliferous era in an endless cycle. Yet, current evidence strongly favors the continued acceleration, making a cyclic universe seem unlikely. Other, more exotic possibilities hinge on physics we have not yet discovered. Could dark matter, which makes up most of the universe's mass but does not interact with light, somehow play a role in a future phase of structure formation? It is a tantalizing but highly speculative thought. Perhaps quantum mechanical processes on unimaginably long timescales could lead to spontaneous creation of new particles or even new universes. The ultimate fate of star formation is inextricably linked to the ultimate fate of the cosmos. It is a story that began with a brilliant flash and a burst of creation, and it appears to be heading toward a quiet, cold, and dark conclusion. Yet the mere fact that we, products of that brief, shining era of star birth, can contemplate this epic timeline from its beginning to its projected end is a testament to the profound power of cosmic inquiry. Our quest to understand star formation has led us to a humbling realization. We are living in the universe's golden age, a temporary window of light and structure in the vast, dark expanse of time. But as we consider the grand forces that shape galaxies and govern the rate of star formation, we must confront the most dominant yet most elusive component of the cosmos, dark matter. This mysterious substance, which reveals itself only through its gravitational pull, does not emit, absorb, or reflect light. It passes through ordinary gas and dust as if they weren't even there, meaning it plays no direct role in the complex chemistry or magnetic physics within a collapsing cloud. Yet, to ignore its influence would be like trying to understand the flow of water in a valley without considering the mountains that surround it. Dark matter provides the fundamental gravitational architecture, the invisible scaffold upon which the entire visible galaxy is built. Its presence is the primary reason galaxies don't simply fly apart as they spin. Its immense, unseen mass creates a deep gravitational well that holds the stellar disk together and governs the motion of everything within it. This overarching influence begins with the dark matter halo, a vast spherical cloud that envelops the galaxy and extends far beyond the visible edge of the stellar disk. The shape and density of this halo are not uniform. Think of it as a gravitational landscape with hills and valleys, but on a cosmic scale. The specific profile of this landscape, how the density of dark matter changes from the galactic center out to the remote outskirts, determines the overall rotation curve of the galaxy. This, in turn, dictates how fast the spiral arms spin and how stable the galactic disk is over billions of years. A galaxy with a particularly massive or concentrated dark matter halo might have a very stable disk, resistant to the bending and warping that can be caused by interactions with neighboring galaxies. This stability can create a more quiescent environment for star formation, allowing gas to cool and settle peacefully. Conversely, a galaxy with a less massive or more irregular halo might be more dynamically active, its disk easily perturbed, potentially triggering waves of star formation through gravitational shocks and compressions. So, while dark matter doesn't touch the gas directly, it sets the stage on which the entire drama of a galaxy's evolution unfolds. This leads us to the frontier of this mystery. Could dark matter's influence extend down to the very smallest scales of star formation? This is a highly speculative but fascinating question. The conventional view is that dark matter is smoothly distributed on the scale of individual molecular clouds. However, some theories suggest that dark matter might not be perfectly smooth. It could clump into smaller structures or even form dense streams and filaments within the larger halo. If these subtle small-scale variations in dark matter density exist, they could, in principle, create tiny, localized fluctuations in the gravitational field. Imagine a molecular cloud drifting through a region of space that has a slightly higher concentration of dark matter. The additional gravitational pull, while incredibly weak, might be just enough to provide the initial nudge that tips a stable cloud toward collapse. It would be an almost imperceptible whisper of gravity, a ghostly hand that gently pushes the first domino in the chain of star birth, while the gravity from the cloud's own gas would still dominate the actual collapse. This dark matter trigger could be a factor in determining exactly when and where within a galaxy new stars decide to ignite. The challenge, of course, is that this idea is extraordinarily difficult to test. We cannot directly map the distribution of dark matter on scales small enough to compare with individual star-forming regions. Our evidence for dark matter comes from its large-scale gravitational effects. Yet, the search for such a connection drives some of the most innovative research in astrophysics. Scientists run sophisticated computer simulations of galaxy formation that include both normal matter and dark matter. By comparing the patterns of star formation in these virtual universes with and without small-scale dark matter clumping, they can look for statistical signatures, perhaps a slight increase in the number of stars born in certain regions or a different distribution of stellar clusters. Finding any correlation would be a monumental discovery, linking the largest, most mysterious component of the universe to the most fundamental process of creation. For now, the influence of dark matter on star formation remains a captivating puzzle. a reminder that the full story of how a star is born may involve forces we are only just beginning to comprehend. And so, after exploring the grand cosmic cycles of stellar birth and the invisible scaffolding of dark matter, we arrive at a mystery that transforms our entire perspective. This isn't just about understanding the universe for its own sake. It's a quest that speaks directly to a deeply human yearning. The drive to unravel the 40 mysteries of star formation is, for many scientists and dreamers alike, ultimately motivated by a single, profound question: are we alone? Every thread we've pulled, from the trigger of collapse to the migration of planets, weaves together into the fabric of this ultimate search. We are not merely cosmic cartographers mapping the heavens. We are detectives seeking clues to the potential for life itself. The grand goal is to find Earth's twin, a world so similar to our own in size, composition, and orbit that it could, in theory, offer a second genesis, a confirmation that the universe is not just a beautiful void but a living, breathing arena. But what does it truly take to find such an analog? It requires far more than just spotting a dot of light in a habitable zone. It demands a complete understanding of the star formation recipe that leads to a system like ours. First, we must start with the right ingredients. The parent molecular cloud must have a specific metallicity, a rich abundance of elements heavier than hydrogen and helium. As we've seen, this metallicity is the legacy of generations of exploded stars, and it directly controls the amount of solid, rocky material available for planet building. A star born from a metal-poor cloud might struggle to form any terrestrial planets at all, let alone one with a robust iron core and a silicate mantle like Earth's. The cloud itself must collapse in a relatively calm environment, avoiding the violent gravitational encounters of a dense cluster that could strip away protoplanetary disks or send nascent worlds careening into interstellar space. The star that forms should be stable and long-lived, a G-type star like our Sun, providing a steady source of energy for billions of years to allow for the slow, patient dance of evolution to unfold. Then, the protoplanetary disk must possess the right conditions and a generous timeline. It needs to be massive enough to supply the material for planets, yet stable enough to last for several million years, giving gas giants time to form in the outer system without migrating destructively inward. The delicate processes of pebble accretion and planetesimal formation must proceed efficiently beyond the snowline, constructing the cores of Jupiter and Saturn. Crucially, these giant planets must act as guardians, not destroyers. In our solar system, Jupiter's massive gravity is thought to have shepherded the inner solar system, potentially deflecting a hail of comets that could have sterilized the young Earth, while also preventing a super-Earth from forming in the region now occupied by our small, rocky world. The absence of such a disruptive migration event is vital. A hot Jupiter barreling through the inner system would have scattered any Earth-like planets into oblivion. Finally, the disk must dissipate in a way that leaves the terrestrial planets in stable, near-circular orbits within the habitable zone. The not too hot, not too cold region where liquid water can persist on a planet's surface. This intricate chain of events highlights a staggering possibility that solar systems like our own, with their well-ordered arrangement and potential for life, might be the exception rather than the rule. The incredible diversity of exoplanets we've discovered, the hot Jupiters, the super-Earths, the planets in chaotic orbits, suggests that our peaceful cosmic neighborhood might be a rare outcome of a very specific and fortunate sequence. Every mystery of star formation we solve adds a variable to the equation of habitability. Understanding magnetic braking tells us about a star's spin and its resulting space weather. Unraveling the initial mass function tells us how common long-lived, stable stars like our Sun are. deciphering planetary migration explains why some systems are orderly and others are violently unstable. The search for Earth's twin is therefore the ultimate test of our knowledge. It forces us to move from simply cataloging exoplanets to truly understanding the physics that creates them. With each new telescope, like the James Webb Space Telescope, we gain the ability to not just detect planets, but to analyze the atmospheres of distant worlds, searching for the chemical signatures of life, biosignatures like oxygen and methane in unlikely combinations. But to interpret those signals correctly, we must first understand the planet's context. Is the oxygen abiotic, produced by the breakdown of water vapor under intense stellar radiation? Is the world a true terrestrial planet or a mini Neptune with a thick, crushing atmosphere? Answering these questions brings us right back to the conditions of its birth. The search for another Earth is not a separate endeavor from the study of star formation. It is the final, magnificent application of everything we are learning. It connects the violent, chaotic beauty of a stellar nursery directly to the serene possibility of a pale blue dot orbiting a distant sun, and in doing so, it transforms our quest from a purely scientific pursuit into a deeply human one, seeking to understand our place in the cosmos by discovering if we have any neighbors. Yet, for all the breathtaking power of our supercomputers and the elegance of our equations, we inevitably run into a fundamental wall, a limitation imposed not by our imagination, but by the very fabric of reality as we understand it through mathematics. This brings us to a deeply humbling mystery: the profound limits of simulation. Can we ever truly create a perfect digital replica of a star's birth? Modern astrophysics leans heavily on these sophisticated computer models, which are nothing short of virtual universes running inside silicon brains. They incorporate the relentless pull of gravity, the fluid dynamics of swirling gas, the invisible architecture of magnetic fields, the transformative power of radiation, and the intricate dance of chemical reactions. These simulations have revolutionized our understanding, allowing us to watch in accelerated time processes that take millions of years, testing our theories in a controlled digital space. We have seen virtual clouds collapse, virtual disks form, and virtual jets erupt in stunning agreement with what our telescopes observe. The progress has been nothing less than extraordinary. However, the complexity of the real universe is almost infinitely greater than anything we can currently hope to model. The core of the problem is a dramatic clash of scales. Imagine trying to simulate the entire weather system of planet Earth. To do it perfectly, you would need to track the motion of every single molecule in the atmosphere, an utterly impossible task. So, you use a grid, breaking the planet into large boxes and calculating the average conditions in each one. This works reasonably well for forecasting a storm system, but it completely misses the small-scale details, like the formation of a single, tiny dust devil. Now, magnify this problem to a cosmic scale. We want to understand how a galaxy like our Milky Way forms stars. But a galaxy is 100,000 light-years across, while the dense core that collapses to form a single star is smaller than our solar system. To simulate the entire galaxy at the resolution needed to see individual stars being born would require tracking more particles than there are atoms in the real universe. It is a computational impossibility. We are forced to make a difficult choice. We can either simulate a large portion of a galaxy with low resolution, missing the fine details of star formation, or we can simulate a single, isolated star-forming cloud with high resolution, but then we ignore the larger galactic environment that influenced its birth in the first place. This challenge of bridging scales is what astrophysicists call the holy grail of computational astrophysics. The dream is to create a model that seamlessly connects the grand, slow dance of galactic evolution with the violent, fast-paced drama of an individual protostar's formation. Imagine a simulation where you could zoom in from a view of an entire spiral galaxy, down through its swirling arms into a specific molecular cloud, through its turbulent filaments, and finally right into the heart of a collapsing core, all within a single, consistent model where the physics at every level is accurately represented. We are not there yet. Each time we try to add more realism, the computational cost skyrockets. Including magnetic fields accurately, for instance, requires solving an additional set of immensely complex equations for every single point in the simulation. Adding radiative transfer, the way light moves through and heats the gas, is another monumental task that can slow a simulation to a crawl. We often have to approximate these processes, using clever but simplified, sub-grid models to stand in for the true physics. It's like trying to paint the Mona Lisa using only a broom. You can capture the general idea, but you'll miss the exquisite detail of the smile. Furthermore, every new discovery from observatories like the James Webb Space Telescope or the ALMA array pushes the limits of what we need to simulate. When we find a new, complex organic molecule in a protoplanetary disk, or observe a bizarre jet structure that our models didn't predict, it forces us back to the digital drawing board. Our simulations are only as good as the physics we put into them, and nature consistently reveals itself to be more inventive than our equations. The ultimate limit may not be just computational power, but also our own fundamental understanding. Are there physical processes in these extreme environments that we haven't even discovered yet? The quest to build a perfect simulation is therefore a deeply symbiotic one. Our models guide our observations by telling us what to look for, and our observations, in turn, challenge and refine our models, driving a cycle of discovery that brings us incrementally closer to a true digital universe, one line of code at a time. And so, after all our sophisticated simulations and elegant theories have been meticulously constructed, the universe has a delightful habit of throwing us a curveball, presenting us with cosmic puzzles that stubbornly refuse to fit into our neatly arranged boxes. These are the unexplained anomalies, the celestial outliers that stand as quiet but insistent reminders that our understanding of star formation is still a work in progress. For every rule we think we've uncovered, there seems to be an exception whispering a more complex truth. Imagine an astronomer observing a young protostar deeply embedded in its dusty cocoon. Using the latest instruments, they measure its luminosity, the temperature of the surrounding gas, and the strength of its outflows. They plug this data into our best models, which have successfully described hundreds of other young stars, and the result is a clear prediction. This object should have a mass of, say, 2 times that of our Sun. But then, a separate measurement, perhaps of the gas dynamics around it, reveals a gravitational pull so strong that it can only be explained if the central protostar is actually 5 solar masses. A discrepancy like this isn't just a small error, it's a glaring signal that something fundamental is missing from our equations. Perhaps our assumptions about how mass is accreted are wrong, or maybe there's a hidden source of energy or a complex magnetic interaction we haven't yet accounted for. These anomalies can take many surprising forms. Consider the enigmatic case of certain protoplanetary disks observed with stunning clarity by the ALMA telescope. Our models predict that as a disk evolves, it should show a smooth, continuous distribution of dust from the star out to its edges. But some disks reveal jaw-dropping structures, vast, concentric gaps that look like the grooves on a vinyl record, or sharp, narrow rings of dust that stand in stark contrast to the empty space around them. While we often attribute these gaps to the gravitational carving of newborn planets, Some of these features are so extreme, so pristine, that they challenge even that explanation. Could they be the signposts of unknown instabilities within the disk itself? Or perhaps they are fossils of a rapid, early phase of planet formation that operated under rules we have not yet deciphered. Then there are the stellar clusters that defy the universal initial mass function we discussed earlier. We expect a predictable ratio of high mass to low mass stars, a pattern seen across the galaxy. But occasionally we find a cluster that is top-heavy, brimming with an overabundance of brilliant, massive stars, or one that is strangely bottom-heavy, populated almost exclusively by small, dim red dwarfs. These oddballs force us to ask, were the conditions in their parent cloud so unique, perhaps with a different level of turbulence, a stronger magnetic field, or an unusual chemical composition, that the very recipe for star formation was altered? It is crucial to understand that these anomalies are not failures of science, they are its lifeblood. Every major leap in our understanding of the cosmos has been triggered by such an outlier. In the late 19th century, the orbit of Mercury presented a tiny, persistent anomaly that Newton's law of gravitation could not fully explain. That small discrepancy became a crucial clue that led Einstein to his theory of general relativity, completely revolutionizing our concept of gravity. The unexplained mysteries of today are the potential revolutions of tomorrow. A protostar that is too massive for its age might be telling us that stars can form through a faster, more violent pathway than we thought. A bizarrely structured disk could be revealing a new type of physical interaction between dust, gas, and magnetic fields that we need to incorporate into our models. By paying close attention to these puzzles, we are essentially following a trail of breadcrumbs left by nature itself, guiding us toward a deeper, more complete theory. The path forward, then, is not to dismiss the oddities but to embrace them with curiosity and rigor. It requires a delicate balance between trusting our well-tested models and having the humility to recognize their limitations. The next generation of telescopes, both on the ground and in space, will be anomaly hunting machines. Their unprecedented resolution and sensitivity will not just confirm what we already know, they will undoubtedly uncover a whole new zoo of bizarre objects and phenomena that we cannot yet imagine. The greatest discoveries in astrophysics often lie not in the confirmation of our predictions, but in the surprise of the utterly unexpected. These unexplained anomalies are the universe's way of keeping us honest and pushing us forward, ensuring that the story of star formation remains a dynamic and ever-evolving narrative, filled with wonder and the promise of new physics waiting just beyond the edge of our current understanding. Having journeyed through these 40 profound mysteries, we now stand back to behold the magnificent tapestry we have helped to weave. The birth of a star, once imagined as a relatively simple act of gravitational collapse, reveals itself as one of the most intricate and interconnected symphonies in all of nature. It is a process where no single instrument plays alone. The deep bass note of gravity provides the fundamental rhythm, the driving force that initiates the entire performance. But it is immediately met by the chaotic, swirling melodies of turbulence, which both supports the grand structure of the cloud and seeds it with the dense fragments of future stars. Woven throughout is the subtle, haunting harmony of magnetism, an invisible force that guides, resists, and sculpts the flow of matter with an unseen hand. Then, as the first protostars ignite, they add the brilliant, percussive bursts of radiation and powerful stellar winds, elements that quickly become dominant themes, actively regulating the pace of creation and destruction around them. And underpinning it all is the complex chemistry of the cosmic nursery, a quiet but essential section that controls the cooling, sets the initial conditions for planets, and even pre-loads the building blocks of potential biology into the system. This is not a simple chain of events, but a dynamic, self-regulating dance where each player influences all the others in a feedback loop that spans from the microscopic scale of dust grains to the grand architecture of entire galaxies. This beautiful complexity means that every mystery we solve does not simply provide an answer and close a door. Instead, it opens a window onto a new landscape of even deeper questions, revealing the endless layers of astrophysical inquiry. Unraveling the trigger of a cloud's collapse leads us directly to the large-scale structure of the galaxy and the history of supernova explosions. Understanding the angular momentum problem forces us to contemplate the incredible physics of magnetized accretion disks and the spectacular phenomenon of bipolar jets. Discovering the correlation between stellar metallicity and giant planets connects the chemical enrichment from long-dead stars to the architecture of newborn solar systems. Each discovery is a thread that, when pulled, connects to countless others, demonstrating that our universe is a profoundly coherent and logical whole, governed by a set of physical laws that are universal in their application. The journey of scientific discovery is therefore a perpetual one, a constant striving toward a horizon that recedes as we approach it, filled with the thrill of not just finding answers, but of learning to ask better, more profound questions. At its heart, the epic story of star formation is the ultimate narrative of how complex structure emerges from primordial chaos. It begins in the vast, dark, and nearly uniform clouds that drift between the stars, where random fluctuations are the only seeds of order. Through the relentless and elegant application of gravity, rotation, and thermodynamics, this chaos is coaxed into form. The random motions of gas are organized into spinning disks. The anonymous dust grains are assembled into planets. The simple hydrogen and helium of the Big Bang are forged into the vast palette of elements that make up our world. This transition from the simple to the complex, from the uniform to the diverse, is a fundamental theme of our cosmos, and star formation is its most vibrant and creative expression. It is the mechanism by which the universe builds the rich structures that allow for galaxies, stars, planets, and ultimately, us. For this is the most humbling and awe-inspiring truth that binds all 40 mysteries together. Our own existence is inextricably tied to the life cycles of distant suns. Every atom of oxygen in the water we drink, every particle of iron in our blood, every nucleus of carbon that forms the foundation of our biology was forged in the nuclear furnace of a star that lived and died long before our sun was born. The very planets that orbit our star, providing a stable home for life, are the direct descendants of the processes we have explored, from the sticky collisions of dust in a protoplanetary disk to the gravitational dance of migrating giant planets that may have shaped our solar system's architecture. When we look up at the night sky, we are not merely looking at distant points of light. We are looking at our cosmic ancestry. We are seeing the factories that produce the elements of our bodies and the nurseries that are, at this very moment, giving rise to new worlds that may one day harbor life of their own. The story of star formation is therefore far more than an astrophysical curiosity. It is the story of our own origins, a continuous thread of cosmic creation that links the primordial universe directly to our ability to ponder its mysteries. From the silent, dark nurseries of molecular clouds to the brilliant ignition of a new star, the process of stellar birth is a testament to the dynamic and creative power of the universe. We have traveled a path of 40 profound mysteries, each one a frontier where our knowledge meets the unknown. We began with the simple, elegant pull of gravity and discovered it is only the first note in a symphony of forces. Turbulence, that beautiful chaos, carves the cloud into stellar seeds. Magnetic fields, invisible and powerful, shape the flow of matter and break the spin that would otherwise tear a young star apart. The spectacular jets that erupt from a protostar's poles are not merely for show. They are essential engines solving the critical problem of angular momentum, allowing the star to grow. And through it all, the humble dust grain, a microscopic speck, acts as a cosmic coolant, a chemical factory, and a building block for worlds. This journey reveals that star formation is not a single process but an intricate dance of physics, chemistry, and dynamics, all playing out on a stage light years across. These 40 mysteries represent the current frontier of our knowledge, but they are not permanent barriers. Each one is a beacon, guiding the next generation of exploration. With every new observation from telescopes like the James Webb Space Telescope, which peers through dust with its infrared eyes, or the Atacama Large Millimeter Array, which maps the cold gas in stunning detail, we gather more pieces of the puzzle. Our computer simulations, while still grappling with the immense range of scales, grow more sophisticated each year, inching closer to a complete digital replica of cosmic creation. We stand on the verge of transforming these mysteries into understood chapters of cosmic history. The strange brown dwarf desert, the violent birth of massive stars, the dynamic migration of planets, these are not unknowable enigmas. They are questions whose answers are waiting to be found, hidden in the light we collect and the equations we solve. The pace of discovery is accelerating, promising a future where the story of a star's birth is as clear and well documented as the life cycle of a butterfly. Yet, this quest is far more than an academic exercise in astrophysics. The drive to understand star formation is ultimately a profound quest to understand our own place in the cosmos. Every mystery we unravel about a distant stellar nursery tells us something about our own origins. The specific metallicity of the cloud that formed our sun dictated the abundance of solid material that became the Earth. The peaceful, isolated nature of our sun's birth, free from the disruptive gravitational tides of a dense cluster, may have been essential for allowing our planetary system to form in its stable, orderly fashion. The water in our oceans, the iron in our blood, the very atoms that constitute our bodies were forged in the hearts of long-dead stars and assembled into our world through the processes we have explored. To study star formation is to conduct the ultimate archaeological dig into our own existence, tracing our lineage back to the heart of a cosmic cloud that collapsed over 4.5 billion years ago. So, let this journey through 40 stellar mysteries ignite a lasting curiosity. The next time you find yourself under a clear night sky, look up at those points of light with a renewed sense of wonder. See them not as static, eternal diamonds, but as individual suns, each with a unique birthday and a dramatic history of creation. Some are young, tempestuous Tauri stars, others are stable middle-aged stars like our sun, and some are the brilliant, short-lived giants that will soon seed the galaxy with new elements. That faint, hazy smudge of the Orion Nebula is not just a cloud. It is a bustling stellar nursery, a living laboratory where the same processes that built our solar system are actively at work right now. The universe is not a static picture but a dynamic, evolving story, and we are both its audience and a part of its narrative. The answers to the remaining mysteries are hidden in that starlight, waiting for the next curious mind, the next powerful instrument, the next leap of imagination.